Hello there, and welcome to Sleepy Cosmic Lens, where curiosity gets comfortable, the universe lowers its voice a little, and even the strangest objects in space are allowed to arrive slowly, without rushing anyone's thoughts. Tonight, we're going to spend some quiet time with one of the most extreme kinds of star ever found. A star that is not really alive in the ordinary stellar sense, not shining calmly like the sun, not burning hydrogen in a steady golden furnace, not sitting politely in the sky, minding its own business, but a collapsed remnant with a magnetic field so intense that it makes ordinary magnets seem like fridge decorations with big opinions. Tonight's question is simple to ask and surprisingly difficult to answer gently. What is a magnetar, really? Before we move too far into the dark, I'd love to know where you're listening from tonight. Are you under a city sky, with only a few bright stars managing to push through the lights? Are you somewhere quieter, perhaps with the Milky Way faintly stretched overhead? Or are you listening in the middle of the day, letting deep space keep you company while the ordinary world carries on around you? And if you feel like sharing, what is the weather like where you are? It feels oddly fitting to ask, because magnetars are all about conditions. Not gentle conditions like a rainy window or a warm blanket, but conditions pushed to such extremes that normal matter, normal atoms, and normal ideas have to be handled very carefully, like a cup of tea filled right to the rim. If you find this kind of slow journey soothing, or if you enjoy letting science become a little quieter at the end of the day, I'd be grateful if you liked the video and subscribed. It helps this calm little corner of the internet reach other people who might also want to fall asleep beside neutron stars, black holes, strange moons, and all the other things that sound slightly alarming until they are explained in a friendly voice. And please do not worry if you drift off somewhere along the way. Magnetars will still be here when you wake up. They have been waiting for thousands of years, some for much longer, and they are not easily offended. So settle in, loosen your shoulders if you can, and let the ordinary room around you become the starting point. Maybe there is a lamp nearby, or a phone resting beside you, or the faint hum of a heater, a fan, a computer, or a street outside. These familiar things live in a world of gentle forces. Gravity keeps your blanket on the bed. Electricity keeps the lights working. A small magnet might hold a note to the refrigerator. The Earth's own magnetic field quietly guides compass needles and helps shield us from charged particles from the sun. It is important, but it is also mild enough that we can forget about it most of the time. You can walk around inside Earth's magnetism all day and not notice it at all, which is very convenient for errands. A magnetar is not like that. A magnetar is what happens when nature takes the idea of a magnet and turns the dial so far past anything familiar that the word magnet almost feels too small. It is a type of neutron star, the crushed core left behind after a massive star explodes as a supernova. Imagine taking more mass than the sun and squeezing it into a sphere roughly the size of a city, not a large country, not a continent, not even a comfortable region on a map. A city, something you could cross by car in less than an hour if it were not made of matter so dense and strange that the comparison becomes useless almost as soon as it is made. A neutron star is already one of the universe's most extreme objects, and a magnetar is a neutron star with a magnetic field of extraordinary strength, often described as about 1,000 times stronger than that of a more ordinary neutron star. That number is easy to say and hard to feel. 1,000 times stronger than an ordinary neutron star sounds dramatic, but ordinary neutron stars are already absurd. Their magnetic fields can be trillions of times stronger than Earth's. So when we talk about a magnetar, we are not speaking about a stronger version of something normal. We're speaking about a stronger version of something that was already far beyond common sense. If Earth's magnetic field is a quiet background hum, and a hospital MRI machine is a very strong, carefully controlled instrument, then a magnetar is not simply the next level. It is an entirely different category. It is the kind of object where you do not casually ask what would happen if you got close, because the honest answer begins with the fact that your atoms would have several complaints, and yet, magnetars are small. That is one of the strangest parts. They are not vast in size like red supergiants. They do not stretch across millions of kilometers. They are not wide, bloated stars glowing at the edge of their lives. They are compact, dim by ordinary visible light standards, and often hidden from casual view. If you could look up at the night sky with only your eyes, you would not point and say, "There it is. That tiny dot is a magnetar." Most of what they reveal comes through X-rays, gamma rays, radio signals, and sudden outbursts that alert astronomers something violent has happened in a place that otherwise seemed quiet. They are small objects with large consequences, which is also how many people describe a misplaced house key. The name itself tells you the main idea: magnetar, magnetic star. It sounds almost straightforward, as if someone in astronomy had a rare moment of naming something clearly. But the simplicity hides a whole complicated life story. A magnetar begins as a massive star, one much heavier than the sun. For millions of years, that star burns through its fuel, building heavier elements in its core, fighting a constant battle between the inward pull of gravity and the outward pressure from nuclear fusion. As long as fusion can provide pressure, the star keeps standing. It is not standing in the human sense, of course, but in the physical sense, holding itself up against its own weight. Then, one day, the core can no longer support the load. The balance breaks. Gravity wins. The star collapses. That collapse is one of the fastest and most violent transformations in the universe. The outer layers of the star are blasted into space in a supernova, spreading elements outward, making a cloud that may one day help form new stars and planets. But the core does not gently fade away. It is crushed down into something incredibly dense. Protons and electrons are forced together. Neutrons dominate. A neutron star is born. In some cases, if the conditions are just right, that newborn neutron star may have an intense magnetic field and rapid rotation. Its interior may behave like a colossal dynamo, amplifying magnetic fields to levels that are difficult to describe without sounding as though science has wandered into exaggeration. If the field becomes extreme enough, we call the object a magnetar. One useful way to think about it is to picture a dying star leaving behind a kind of locked box. Inside that box is gravity, density, rotation, heat, and magnetic energy, all squeezed into a space so small that the object becomes more like a cosmic engine than a normal star. A magnetar does not need to shine because of ordinary fusion. It is powered largely by the decay and rearrangement of its magnetic field. The magnetic field is not just a decoration around the star, it is a reservoir of energy. It twists, it stresses the crust, it can store enormous tension. And sometimes when that tension changes suddenly, the magnetar releases bursts of high-energy radiation. This is where magnetars become especially dramatic. Many were first understood through strange, high-energy signals called soft gamma repeaters and anomalous X-ray pulsars. The names sound technical, but the basic idea is approachable. Astronomers saw objects producing repeated bursts of gamma rays and X-rays, or shining in X-rays more strongly than expected. These signals did not fit neatly with ordinary pulsars. A normal pulsar is also a neutron star, usually detected because it spins and sweeps beams of radiation across Earth like a lighthouse. Magnetars can spin too, but their unusual brightness and sudden flares suggested something else was feeding the energy. Over time, the magnetic explanation became the key. The star's magnetic field was not merely strong, it was the main actor. There are only a few tens of confirmed or candidate magnetars known, which makes them rare in our catalogs, though not necessarily rare across the whole galaxy. The Milky Way is large, dusty, busy, and not always generous with clear views. Some magnetars may be hidden from us. Others may be quiet at the moment, waiting between bursts. Astronomers often find the universe not by looking for things that behave politely, but by noticing when something misbehaves: a sudden flash, a strange pulse, an X-ray source that should not be that bright, a gamma ray burst that repeats instead of behaving like a one-time explosion. Space, for all its emptiness, has a way of occasionally knocking on the instruments. One of the most famous knocks came on December 27, 2004. From a magnetar called SGR 180620. In a fraction of a second, it released an enormous flare of gamma rays so bright that it affected instruments in space and even disturbed Earth's upper atmosphere. The object was located far across the Milky Way, tens of thousands of light years away, and yet the burst was still strong enough to be noticed here. That is the kind of fact that makes you pause for a moment. Something the size of a city sitting on the far side of the galaxy shifted its magnetic stress and sent a flash across space that touched our planet's ionosphere. No danger to us at that distance, but certainly a reminder that small does not mean weak when the small thing is a magnetar. Still, this opening moment is not the place to hurry into every violent detail. There will be time to talk about starquakes, giant flares, twisted magnetic fields, strange crusts, and the rather unfriendly question of what would happen to a person who wandered too close. For now, it is enough to begin with the feeling of scale. A magnetar is not just a dead star. It is a dead star with stored energy. It is not just dense, it is dense and magnetic. It is not just a leftover. It is an active remnant, a stellar corpse that can still crack, flare, pulse, and remind the galaxy that death in astronomy does not always mean silence. That phrase, dead star, can be a little misleading. It makes the object sound cold and finished, like a burnt match after the flame has gone out. But neutron stars are not simple ashes. They can be extremely hot when they are young. They can rotate. They can have magnetic fields strong enough to shape the space around them. They can emit radiation for thousands of years. They can change suddenly. The star that made them may be gone, but the remnant is not passive. It is more like a compressed memory of the star's last moment, a core that kept the violence of collapse, the spin of the original star, and the magnetic field, all packed into a new form. This is part of what makes magnetars so fascinating. They sit at the crossing point of several big questions. What happens to matter when gravity squeezes it beyond anything we can reproduce on Earth? How do magnetic fields behave when they are stronger than the fields in any laboratory? Why do some neutron stars become ordinary pulsars while others become magnetars? How does a crust made under such pressure crack? What happens inside an object where the rules of nuclear physics, plasma physics, quantum theory, and relativity all crowd into the same very small room and refuse to take turns? Scientists do have working models. They're not simply shrugging at the sky, though one imagines that shrugging has happened over the years.
Yeah, it is.
Magnetars are generally understood as
really
neutron
beautiful.
stars whose magnetic fields dominate their energy output. Their surfaces in magnetospheres can become twisted. Their crust can be stressed by magnetic forces. Bursts may happen when that stress is released, a little like a quake, though the material involved is not rock as we know it. The comparison helps, but only up to a point. A starquake on a magnetar is not a small tremor under your feet. It is a rearrangement in one of the strongest magnetic environments known, and the energy release can travel across the galaxy as high-energy light. From a bedtime point of view, magnetars may seem like odd company. They are not gentle. They are not quiet in the usual sense. They are certainly not the kind of object you would choose as a neighbor, but they are strangely good for slow thinking, because they ask us to hold two ideas at once. The universe can be calm from far away and extreme up close. The night sky can look still, while hidden within it are objects twisting magnetic fields, cracking crusts, and sending signals through space. We lie here in ordinary gravity, under ordinary blankets, in ordinary rooms, while somewhere in the galaxy, a remnant smaller than a city may be carrying a magnetic field so strong that it changes the behavior of matter itself. There is comfort in that distance. Not because the universe is safe in every direction, but because it has structure. The dangerous things are far away. The signals arrive as information. We do not meet the magnetar directly. We meet it through detectors, through careful measurements, through years of patient astronomy. Humans are very small beside these objects, but we are also very good at noticing. We build instruments that catch X-rays above the atmosphere. We compare pulses. We measure spin periods of several seconds, watch them slow over time, and use that slowing to estimate magnetic strength. We turn flashes into data into models, and models into stories we can understand at midnight, without needing to become a neutron star ourselves, which is considerate of science. So when we ask, what is a magnetar really? We're asking more than a definition. We're asking how a star can die and still remain powerful. We're asking how magnetism, usually so gentle in daily life, can become the dominant force around a collapsed core. We're asking how matter behaves when squeezed into densities that make everyday objects seem almost empty. We're asking why the universe sometimes hides its greatest strength in very small places. And perhaps we're also asking why these distant, violent things can feel peaceful to learn about when explained slowly enough, with enough room between the facts for the mind to rest. For tonight, picture one small object in the dark. It is not glowing like a familiar star. It is not wide enough to dominate a constellation. It may be buried behind dust, known mostly by its X-rays, its bursts, its strange steady pulse. Around it, magnetic field lines twist through space. Beneath them, a crust harder than ordinary matter can easily describe holds enormous tension. Inside, physics becomes dense, hot, and deeply unfamiliar. It is a remnant, but not an ending. It is a lighthouse, a locked spring, a collapsed core, and a warning label written in gamma rays. To understand a magnetar, we first need to spend a little time with the kind of object hiding underneath that powerful name. Before the flares, before the twisted magnetic field, before the sudden bursts of X-rays and gamma rays crossing the galaxy, there is a neutron star. And a neutron star is already so extreme that it almost feels unfair for the universe to make an even stranger version of it. It is like being introduced to a storm and then being told, very calmly, that this is only the light drizzle before the real weather arrives. A neutron star begins where an ordinary star's life has gone completely beyond ordinary. Not a small star like the sun, which will one day swell, shed its outer layers, and leave behind a white dwarf, but a much more massive star. A star that lived fast, burned fiercely, and spent its fuel with the confidence of someone who has not checked the bill yet. For millions of years, it shines by fusing lighter elements into heavier ones. Hydrogen becomes helium, helium becomes carbon and oxygen. In the deepest layers, if the star is massive enough, the fusion chain continues, building heavier and heavier elements until the core contains iron. Iron is a turning point. It is useful in bridges, frying pans, and the occasional medieval sword. But inside a massive star, it is the sign that the easy energy is gone. Fusing iron does not release energy in the same helpful way. The star has reached a kind of physical dead end. Until that moment, the star has been holding itself up through a balance. Gravity pulls inward, trying to crush everything toward the center. Fusion pushes outward, producing pressure from the star's hot interior. For most of the star's life, those two sides stay in a rough truce. Not a peaceful truce exactly, because a massive star is not a quiet sitting room, but a working balance. Then the core runs out of the kind of fuel that can support it. The outward pressure falls. Gravity, which has been waiting patiently for millions of years, wins. The collapse is astonishingly fast. The core falls inward at a huge fraction of the speed of light. Matter that once filled a region thousands of kilometers across is squeezed down into something only about the size of a city. Electrons and protons are forced together under the pressure, forming neutrons and releasing a flood of neutrinos. The outer layers of the star rebound and blast outward in a supernova, spreading heavy elements into space. For anyone far away, if far away can mean safely many light years away, the star would briefly become one of the brightest things in its galaxy. For the core, there is no gentle farewell. It becomes something compact, dense, and almost impossibly strange. That leftover core is the neutron star. It is not a star in the familiar sense anymore. It is not calmly fusing hydrogen in its center. It does not have a glowing surface like the sun's, with boiling plasma and sunspots, and a pleasant chance of producing a summer afternoon. It is the collapsed heart of a dead massive star, packed so tightly that ordinary comparisons start to creak. People often say that a teaspoon of neutron star material would weigh billions of tons on Earth. That is a useful image, although a teaspoon is really not the right household tool for neutron star matter. You cannot scoop it, store it, or pass it around at a dinner party, unless the dinner party has taken a deeply unfortunate turn. The density is the point. In ordinary matter, atoms are mostly empty space. A tiny nucleus sits in the center. Electrons occupy a much larger surrounding region, and the whole thing behaves as if it is solid because of electromagnetic forces, not because it is packed edge to edge with stuff. In a neutron star, that empty space has been mostly crushed out. The matter is pushed toward nuclear density, meaning it resembles the density inside atomic nuclei, but spread across an object many kilometers wide. That is one reason neutron stars are so important to physicists. They are natural laboratories for matter under pressure we cannot reproduce in any Earth-based laboratory. If atoms are like roomy houses with very tiny furniture, neutron star matter is what happens when the houses, the furniture, the streets, and much of the neighborhood are compressed into one crowded, stubborn block. A typical neutron star may have a mass greater than the sun's, squeezed into a sphere perhaps around 20 kilometers across, though the exact size depends on the physics of dense matter, which scientists are still working to understand. That means its gravity is fierce. If you could stand on the surface, which you cannot for several very strong reasons, gravity would be billions of times stronger than what you feel on Earth. A small object dropped from a height would hit the surface at an enormous fraction of the speed of light. Even light itself has to work hard to escape. The star is not a black hole because it has not collapsed past the point where escape becomes impossible, but it is close enough to the edge of extreme gravity that space and time around it are strongly curved. It is a compact object in the truest sense, a place where the universe has tightened its grip. Now, inside this already extreme object, we need to notice something that will matter very much for magnetars. The neutron star has a magnetic field. Most neutron stars do. They are not just dense balls of matter, they are rotating, magnetized remnants. Some rotate slowly by human standards, once every several seconds. Others spin many times per second. Young neutron stars can rotate astonishingly fast because of conservation of angular momentum. This is the same basic idea that makes an ice skater spin faster when pulling in their arms. A massive star's core had rotation before collapse, and when it shrinks dramatically, that rotation speeds up. The result can be a city-sized object spinning with the energy and regularity of a cosmic engine. If the magnetic field is not aligned with the rotation axis, beams of radiation can sweep through space as the neutron star spins. When one of those beams crosses Earth, we see pulses. This is a pulsar. The lighthouse comparison is common because it works rather well. A lighthouse does not flash because the lamp is turning on and off. It flashes because a rotating beam points toward you at regular intervals. A pulsar is similar, except the lighthouse is a dead stellar core with powerful magnetic fields, and the sea is interstellar space, and the boat is our telescope, which is not a perfect comparison, but it gets us safely to shore. Pulsars were discovered in 1967, and at first, their incredibly regular signals were so surprising that they caused a fair bit of excitement and confusion. The pulses arrived with such steady timing that they looked artificial, at least for a brief moment of honest scientific bewilderment. The first source was even jokingly labeled LGM-1 for little green men, before it became clear that nature had invented a more interesting explanation than polite aliens sending radio ticks. These were neutron stars. Their pulses were not messages, but rotation. And once astronomers knew what to look for, more pulsars appeared in the data. The dead stars were not silent. They were keeping time. A magnetar belongs to this same broad family of neutron stars, but it is not simply a regular pulsar with a stronger personality. It has a magnetic field so intense that the field itself becomes the main source of its activity. For ordinary pulsars, much of what we observe is powered by rotation. The star spins. Its magnetic field channels particles. Radiation beams sweep outward, and over time the star gradually slows as it loses rotational energy. A magnetar also rotates and slows, but its strange behavior is powered mostly by magnetic energy. Its magnetic field is not just strong enough to guide particles, it is strong enough to stress the star's crust, heat regions of the surface, twist the surrounding magnetosphere, and produce bursts that can suddenly brighten the object in X-rays and gamma rays. That is why the phrase magnetic heart is useful. The magnetar's power is not only on the surface. The magnetic field likely threads through the star and its surroundings, storing energy in ways that are still being studied. Deep inside, under layers of dense matter, the field may be wound and tangled. Near the surface, the field can push and pull against the crust. Above the surface, charged particles move along field lines, creating a magnetosphere unlike anything around Earth. The whole object is shaped by magnetism. It is not a dead star that happens to have a magnetic field. It is a dead star whose remaining life is controlled by that field. The surface of a neutron star is also not like the surface of a planet. It is not soil, rock, sand, or ice. The outer crust is made of atomic nuclei and electrons arranged under intense pressure. Go deeper and the nuclei become more neutron-rich. Deeper still, the matter changes again, and scientists discuss possibilities such as neutron superfluidity, superconducting protons, and exotic phases of nuclear matter. These are not decorative details. They matter because they influence how heat moves, how the magnetic field evolves, how the crust breaks or shifts, and how the star cools over time. In a magnetar, the internal magnetic field may be so powerful that it slowly rearranges itself, pushing stresses into the crust until something gives. It helps to imagine the neutron star as an object with two kinds of memory. One memory is gravitational. It remembers the collapse that made it, the violent compression of the old stellar core, the supernova that threw away the rest of the star. The other memory is magnetic. It carries some transformed version of the magnetic field of the original star, amplified and reshaped by collapse, rotation, and the complex motion of conducting matter. In a magnetar, that magnetic memory becomes enormous. It is as if the star's final moment left behind not just a compact remnant, but a wound-up magnetic spring. A normal magnet in your house has field lines that loop from one pole to the other. They can hold up a photo, help close a cupboard door, or create a small moment of panic when you cannot find where you put it. The magnetic field around a magnetar is not a larger version of that domestic convenience. It is a region where electromagnetic forces become extreme enough to affect radiation, particles, and perhaps even the vacuum in strange quantum ways. Very close to the magnetar, atoms would not behave normally. Electron clouds would be distorted. Chemistry, which depends on the usual arrangement of electrons around nuclei, would be overwhelmed. Matter as we know it expects a quieter neighborhood. This is one of the reasons magnetars are so compelling. They take something familiar, magnetism, and reveal its most extreme possible form. You have met magnetism many times: a compass needle turning north, a fridge magnet holding a shopping list, the magnetic strip on an old bank card, the hum of electric motors, the protection Earth gets from its magnetosphere as charged particles from the sun are guided around our planet. Magnetism is woven through daily life, but usually in ways that feel manageable. A magnetar reminds us that the same force, under different conditions, can dominate an entire star. The rotation of magnetars adds another layer. Many known magnetars rotate more slowly than young ordinary pulsars, often with periods of a few seconds. That may sound fast if you imagine a city-sized object turning once every 5 or 10 seconds, which it is. But compared with some pulsars spinning many times each second, magnetars are relatively slow. Their strong magnetic fields act like brakes. As the star rotates, the field interacts with charged particles and radiation, carrying away energy and angular momentum. The magnetar spins down over time. By measuring how quickly its rotation slows, astronomers can estimate the strength of the magnetic field. It is a bit like judging the strength of an invisible hand by watching how quickly it slows a spinning top. Those timing measurements are one of the quiet triumphs of astronomy. We cannot visit these objects. We cannot place a probe on the surface. We cannot scoop up neutron star crust and bring it back, which is good because customs forms would become complicated. Instead, astronomers watch pulses, measure periods, track tiny changes, and combine those observations with theory. A magnetar's heartbeat, if we want to use that word gently, is its rotation. Each pulse carries information. Each slowdown hints at the magnetic field. Each sudden burst suggests something changed in the star or in the space just around it. Over time, the pattern becomes a biography. Some magnetars have been found inside or near supernova remnants, the expanding clouds left behind by stellar explosions. This makes sense if magnetars are young neutron stars born from massive stars. The remnant is like the smoke around the candle after the flame has changed form. Though in this case the candle was a massive star, and the smoke is a glowing, expanding shell of gas spread across light years. But not every magnetar sits neatly inside an obvious remnant. Some are isolated. Some may have traveled from their birth sites, kicked by asymmetries in the supernova explosion. A neutron star can receive a powerful natal kick, sending it racing through space at hundreds of kilometers per second. So, a magnetar may not always be found where its parent star died. It may be roaming, carrying its magnetic heart through the galaxy like a very unfriendly ember. There's also the question of age. Magnetars are usually thought to be relatively young as neutron stars go, often thousands to tens of thousands of years old in their active phase. Their magnetic fields decay over time, releasing energy and powering their unusual emission. That decay is not like a battery draining smoothly in a remote control. It involves the complex evolution of fields inside dense matter, heat moving through the crust, stresses building and relaxing, and currents flowing in the magnetosphere. The magnetar may have quiet periods, then sudden outbursts. It may fade, brighten, and surprise astronomers. In other words, even a dead star can have moods, though it would be best not to mention that too loudly near the physics department. To make the idea more grounded, picture an object roughly the width of a city, perhaps small enough to fit between the edges of a large metropolitan area, but containing more mass than the sun. Its gravity crushes matter into states that do not exist naturally on Earth. Its surface is hot by human standards, though cooling compared with its birth. Its crust is incredibly strong, yet not immune to stress. It spins. It slows. Around it, a magnetic field extends into space with a strength that makes familiar magnetic fields seem like whispers. This is the base object. This is the body of the magnetar. The flares and bursts are not separate magic tricks. They're consequences of this compact magnetic remnant trying to settle, cool, twist, and age. That dead star nature also helps explain why magnetars are not found everywhere. You need a massive star first. Massive stars are less common than small stars, and they live short lives. They often form in star-forming regions, burn through their fuel quickly, and die in supernovae. Only some of their collapsed cores become neutron stars. If the core is too massive, it may become a black hole. Among neutron stars, only some become magnetars, so each magnetar is the result of a selective chain of events. A star had to be massive enough to collapse, but not in exactly the way that made a black hole. The conditions had to allow a neutron star. The magnetic field had to become extraordinary. The object then had to be active or visible enough for us to detect it. By the time we identify one, we're looking at a rare outcome of a violent life. Still, the galaxy may contain many more quiet magnetars than we know. Some may have cooled and faded. Some may no longer burst often. Some may be hidden behind dust or too faint for our instruments under normal conditions. Others may reveal themselves only briefly during outbursts. This makes magnetar astronomy a little like listening in a dark house for an occasional creak. The absence of sound does not mean the house is empty. It may simply mean the old floorboards are waiting for the right temperature change. The universe does not always announce its rare objects politely on a schedule. A dead star with a magnetic heart is also a reminder that stars do not simply vanish when their main lives end. The sun's eventual remnant, a white dwarf, will cool slowly for ages. Massive stars can leave neutron stars or black holes. These remnants are not afterthoughts. They shape their surroundings, enrich the galaxy, and reveal physics at the edge of what matter can do. A magnetar is one of the most dramatic examples because its energy comes from a field we can understand in ordinary life, at least in principle, but pushed to a scale that feels almost unreal. It is both familiar and alien. Familiar because magnetism turns compass needles. Alien because magnetism there can crack a star. Maybe that is the gentlest way to hold the idea for now. A magnetar is not a separate species of cosmic monster floating outside the known rules. It is a neutron star, one of the possible remains of a massive star's collapse. It has mass, radius, rotation, gravity, heat, and a crust. It obeys physics, though much of that physics is difficult and extreme. What sets it apart is the magnetic field, the stored energy wound through and around it. That field is what changes a compact remnant into a magnetar. It is the heart of the story, not because the star has a heart in the living sense, but because magnetism is what keeps its strange activity going long after fusion has stopped. A magnetar's birth begins inside a massive star, long before anyone could call it a magnetar. For most of its life, that star is not strange in the way a magnetar is strange. It is enormous, hot, bright, and busy, but it is still doing the basic work that stars do. It is holding itself together through a balance between gravity and pressure. Gravity wants everything to fall inward. Heat and radiation from nuclear fusion push outward. For millions of years, the star manages this balance with impressive confidence. like someone carrying far too many cups of tea across a room and somehow not spilling any of them. It may look steady from far away, but inside, the star is constantly changing. The first fuel is hydrogen. Deep in the core, hydrogen nuclei fuse into helium, releasing energy that keeps the star shining. In a star like the Sun, this stage lasts for billions of years because the Sun spends its fuel at a measured pace. A massive star does not. It is brighter, hotter, heavier, and much less patient. It burns through fuel quickly. What takes the Sun billions of years may take a massive star only millions. That sounds long from a human point of view, but in the life of the galaxy, it is almost rushed. Massive stars are the dramatic guests at the cosmic gathering. They arrive bright, live intensely, make a lot of heavy elements, and leave in a way that ensures nobody forgets they were there. As hydrogen runs low in the core, the star begins fusing helium into heavier elements. Later, if the star is massive enough, it moves through carbon, neon, oxygen, and silicon burning. These are not separate little fires sitting neatly in the middle like candles on a cake. They happen in layers like shells around the core, with different kinds of fusion taking place at different depths. The star becomes something like an onion, though an onion several times the mass of the Sun, hotter than almost anything you would want near a kitchen, and very poor in soup. Each layer is a different stage of nuclear work. Each stage produces new elements. Each stage also brings the core closer to trouble. The trouble is iron. Iron is special because fusing it does not give the star useful energy. Earlier fusion stages release energy and help support the star against gravity. Iron does not help in the same way. Once the core has built up enough iron, it is like the star has reached the end of a road. The core cannot keep producing the pressure it needs. Gravity, which has been pulling the whole time, suddenly has much less opposition. This is the moment when a massive star's life turns from slow evolution to catastrophe. The collapse begins in the core. It happens with terrifying speed. The inner region of the star, heavier than the Sun, starts falling inward. Electrons are pushed into protons, forming neutrons and releasing neutrinos. Those neutrinos are tiny, ghostly particles that interact only weakly with matter, so they stream outward in huge numbers. In fact, most of the energy of a core collapse supernova leaves as neutrinos, which is one of those facts that makes the visible explosion seem like the dramatic part, even though much of the energy has already escaped quietly through particles that barely touch anything. The universe is very good at hiding the main event behind the brightest effect. As the core collapses, density rises to nuclear levels. The material cannot be squeezed in the ordinary way anymore. The inner core stiffens and rebounds, while the outer parts are still falling inward. A shock wave forms, trying to move outward through the star. The details of how that shock is revived and how the explosion succeeds are complicated, involving neutrinos, turbulence, rotation, magnetic fields, and layers of stellar material. Scientists model these events with powerful computers, because this is not the sort of process anyone can recreate in a laboratory. You cannot put a massive star in a test chamber and say, "Gently, collapse, please." We have to study nature's own explosions and build the physics from there. When the supernova succeeds, the outer layers of the star are blasted into space. Elements forged inside the star and elements made during the explosion are thrown outward. Oxygen, carbon, silicon, iron, and other materials begin their long journey into the surrounding interstellar medium. One day, some of that material may become part of new stars, planets, moons, rocks, oceans, or living things. A supernova is destruction, yes, but it is also distribution. It is the galaxy's most dramatic way of returning ingredients to the shelf. The star dies, and space receives the pieces. At the center, the core remains. If it is not massive enough to collapse into a black hole, it becomes a neutron star. This newborn neutron star is unimaginably hot, dense, and compact. It may begin its life rotating rapidly. It may also carry a magnetic field inherited from the original star and strengthened by collapse. Magnetic field lines that were spread across a huge stellar core are compressed into a much smaller volume. And when you squeeze the region through which a magnetic field passes, the field can become much stronger. That alone can make a neutron star magnetic beyond ordinary experience. But for a magnetar, the field must become even more extreme. This is where the story becomes an active area of research. Astronomers know that magnetars are neutron stars with extraordinary magnetic fields. The harder question is exactly how those fields become so powerful. One idea is called the dynamo model. In this picture, the newborn neutron star is rotating very quickly, perhaps with a period of only a few milliseconds. The inside of the young object is incredibly hot and turbulent. Conducting fluid moves, rotates, and convects. Under the right conditions, that motion can amplify magnetic fields, rather like a dynamo in a power station or a bicycle light. Except the bicycle is a newborn neutron star, and the rider is gravity having a very intense day. Rapid rotation and churning interior motion may wind up and strengthen the magnetic field until it reaches magnetar levels. This idea has an attractive simplicity. A very young neutron star is hot. It can rotate rapidly. Its interior can move. Moving, electrically conducting material can generate and amplify magnetic fields. Put those ingredients together, and you have a possible way to make a magnetar. But nature rarely stops after offering one possible explanation. There are questions. Do all magnetars require extremely rapid initial rotation? If they're born spinning extremely fast, should their supernova remnants show evidence of extra energy from that rapid rotation? Some studies of supernova remnants associated with magnetars have not found clear evidence that all of them were powered by ultra-fast newborn neutron stars. That does not destroy the dynamo idea, but it suggests the story may not be the same for every magnetar. Another possibility is that some magnetars descend from stars that already had unusually strong magnetic fields in their cores. In this fossil field idea, the magnetar field is not built entirely from rapid newborn rotation. Instead, it is inherited, compressed, and preserved from a strongly magnetized progenitor star. The massive star may already have had a powerful internal field, and when the core collapsed, that field was squeezed into the neutron star. Compression can make it enormous. This explanation may work especially well for some magnetars, though it also has questions of its own. How common is a strongly magnetized massive star? How does the field survive the complicated life of the star? How is it arranged after collapse? The answers are still being refined. There are also hybrid possibilities. A star might begin with a strong field, then collapse into a rapidly rotating neutron star whose internal motions amplify it further. Fallback material from the supernova may also play a role in some scenarios. After the explosion, not all material necessarily escapes. Some of it can fall back toward the newborn neutron star, adding mass, changing rotation, and interacting with magnetic fields. The early seconds and minutes after a supernova are messy. Matter is flying outward. Some matter may be falling inward. Neutrinos are streaming. The neutron star is cooling. Its crust has not settled into the older form it will have later. Magnetic fields may be winding, twisting, and rearranging. It is less like a clean birth announcement and more like an entire physics department being dropped into a thunderstorm. One important detail is that magnetar birth is brief in the key stages. The massive star may live for millions of years, but the collapse of the core happens in seconds. The formation of the neutron star happens almost immediately on astronomical timescales. The amplification or organization of the magnetic field may happen in the first seconds, minutes, or early life of the object. A whole future is set very quickly. After all that long stellar life, after all those years of fusion, the final identity of the remnant can be decided in a moment so short that it would fit inside a human breath. Space often works this way. It spends ages preparing, then changes everything at once. The newborn magnetar may then influence the explosion around it. This is especially important in discussions of some superluminous supernovae far brighter than typical ones. In some models, a rapidly spinning newborn magnetar injects energy into the expanding debris, making the explosion shine much brighter for longer. As the magnetar slows down, it can transfer rotational energy into the surrounding material. The result may be a supernova so luminous that it can be seen across enormous cosmic distances. Not every magnetar birth produces such a display, and not every bright supernova has the same engine, but the magnetar-powered supernova idea has become an important part of modern astrophysics. For the quieter magnetars in our own galaxy, the birth site may be marked by a supernova remnant. These remnants are expanding clouds of gas, often glowing in radio, optical, or X-ray light. They are the scattered outer layers of the dead star. If a magnetar sits near the center of such a remnant, astronomers have a strong clue that it was born in that explosion. But things are not always neat. Neutron stars can receive kicks during birth. If the explosion is asymmetric, if one side pushes harder than another, the newborn neutron star can be launched away at high speed. Over thousands of years, it may travel far from the center of the remnant. Sometimes the remnant fades or blends into the surrounding interstellar medium. Sometimes the association is uncertain. Astronomers then have to reconstruct a history from positions, distances, ages, and motion, which is a bit like trying to work out where a firework was launched after the smoke has drifted across the field. The kick itself is another reminder of how violent the birth is. A neutron star is not gently placed into space. It may be thrown. Some neutron stars move at hundreds of kilometers per second. A magnetar can carry its intense magnetic field through the galaxy, moving away from the cloud that made it. From Earth, we see a compact object and perhaps a surrounding remnant, but the real event was dynamic, asymmetric, and harsh. The star did not merely die. It collapsed, rebounded, exploded, and fired its core into the dark. There is also the matter of spin. A newborn neutron star may rotate rapidly, but observed magnetars usually rotate more slowly than many young pulsars, often once every few seconds. That seems surprising at first. If rapid rotation helps create a magnetar, why are magnetars not all spinning at wild speeds today? The answer is that strong magnetic fields are very effective at slowing rotation. The magnetar loses rotational energy as its magnetic field interacts with the surrounding environment and carries energy away. Early in life, especially if the field is extremely strong, the spin down can be rapid. So a magnetar may be born spinning quickly and then slow dramatically. It is a little like a toy top that begins with a sharp, fast spin but is being braked by an invisible hand much stronger than friction on a floor. As the young magnetar cools, its crust forms. This crust is not rock, but a layer of dense nuclear matter under conditions far beyond Earth. The magnetic field threads through and around it. Over time, the field evolves, and that evolution can stress the crust. The star is no longer in the supernova moment, but it is not peaceful either. Magnetic energy remains locked inside and outside the star. The object may spend thousands of years releasing that energy through steady X-ray emission, bursts, and rare giant flares. The violence of birth becomes the stored tension of later life. A magnetar is, in that sense, a supernova's afterthought that refuses to be quiet. It may help to compare this to a bell. Strike a bell once, and the sound continues after the blow. The supernova is the strike. The magnetar is not the sound exactly, but it is the ringing remnant, the compact thing still carrying energy from the event that made it. The difference, of course, is that a bell does not have a magnetic field strong enough to rearrange its surroundings. And if yours does, it may be time to leave the room, but the idea is useful. A magnetar's later behavior is tied to its birth. The strength and shape of its magnetic field, its rotation, its mass, its internal temperature, and even its position in space all come from that first violent formation. Scientists still debate why only some neutron stars become magnetars. Perhaps the parent star's mass matters. Perhaps its rotation matters. Perhaps its magnetic field before collapse matters. Perhaps binary companions play a role by stripping material, spinning the star up, or changing its late-life evolution. Massive stars often live with companions, and binary interactions can dramatically alter how a star evolves. A companion can remove outer layers, transfer angular momentum, or change the core's rotation before collapse. In some cases, the path to a magnetar may not be a lonely one. The dead star with the magnetic heart may owe part of its identity to another star that once orbited nearby. This is one of the reasons magnetars remain so interesting. Their birth is not a solved recipe with neat measurements and a single instruction card. It is a set of possible routes through massive star evolution, collapse, rotation, magnetic fields, and explosion. Different magnetars may have different histories. Some may come from rapidly rotating newborn neutron stars. Some may preserve strong fossil fields. Some may be shaped by fallback. Some may come from binary systems. Nature may not be using one recipe. It may have several. And astronomers are still sorting out which ingredients matter most. Even with these uncertainties, the broad picture is clear enough to follow gently. A massive star runs out of fuel in its core. Gravity collapses the center. The outer layers explode as a supernova. the core becomes a neutron star. Under certain conditions, the newborn neutron star develops or retains an extraordinary magnetic field. That field turns the object into a magnetar. What begins as a star many times heavier than the sun ends as a sphere the size of a city wrapped in magnetic power. The scale of the transformation is almost absurd. A giant star becomes a compact remnant. Fusion gives way to magnetism. A bright life ends, and a different kind of activity begins. There is something quietly humbling about that. The magnetar is not an alien object dropped into the universe from outside physics. It is made by ordinary stellar evolution pushed to its most extreme end. It comes from the same broad process that fills galaxies with chemical elements and creates the raw materials for planets. The calcium in bones, the iron in blood, the oxygen in air, all connect in some way to the lives and deaths of stars. Magnetars are part of that same family story. Just the relative who arrives late, says very little, and can release more energy in a fraction of a second than the sun emits in a long stretch of time. Every family has one. So when we imagine the birth of a magnetar, we should not picture a calm star simply turning into a stronger star. We should picture collapse. We should picture the core of a massive star losing support and falling inward. We should picture matter crushed toward nuclear density. We should picture neutrinos flooding outward, a shockwave struggling through in falling layers, and the outer star being torn apart. We should picture a newborn neutron star, hot, spinning, and magnetized, with its field amplified, compressed, or inherited into something extraordinary. Then as the explosion expands and fades, the magnetar remains at the center or races away from it, carrying a field so strong that it will shape everything the object does next. The magnetic field around a magnetar is the part of the story where ordinary language begins to struggle a little. We can say that it is strong, but strong is the same word we use for a cup of coffee, a stubborn suitcase zipper, and a person who manages to stay calm while assembling flat-pack furniture. It does not quite carry enough weight for a dead star whose magnetic field may reach about 1,000,000 billion Gauss. So before we try to imagine what that means, it may help to begin with a familiar kind of magnetism, the quiet kind, the kind that lives around us every day without turning the room into a physics emergency. Earth itself is magnetic, not dramatically magnetic, not in a way that pulls spoons across the kitchen, but enough to guide compass needles and shape a vast magnetic bubble around our planet. That bubble, the magnetosphere, helps steer charged particles from the sun and gives us auroras when those particles interact with the upper atmosphere. It is one of those planetary features we usually forget about because it works best when we do not have to think about it. Earth's magnetic field is gentle at the surface, roughly around half a Gauss in many places, though it varies from location to location. A refrigerator magnet is much stronger nearby, perhaps around 100 Gauss, which is enough to hold up a shopping list, a postcard, or a very optimistic child's drawing of a horse that looks more like a table with ears. A hospital MRI machine is stronger still. MRI fields are measured in Teslas rather than Gauss, and 1 Tesla equals 10,000 Gauss. A common clinical MRI might operate at 1.5 or 3 Tesla, while some research machines go higher. These machines are powerful enough that metal objects must be kept away, and anyone entering the room has to be careful about implants, tools, jewelry, and anything that might decide to become a projectile. That is the strongest magnetic environment most people can easily imagine. It is carefully engineered, carefully shielded, and placed inside a building with warning signs. A magnetar makes even that seem like a polite suggestion. The numbers used for magnetars are so large that they can become sleepy in the wrong way.
Is it nice there?
Not soothing, but meaningless.
Yeah, it is.
1,000,000 billion Gauss.
It's really
a
beautiful.
quadrillion Gauss. 1014 or 1015 Gauss. These are the correct kinds of numbers, but the mind does not naturally hold them. It is like being told the ocean contains a great many spoons. At some point, the quantity stops feeling like quantity and turns into fog. So instead of trying to stare directly at the number, we can approach it by asking what such a field does. A magnetic field is not a material object. You cannot put it in a jar, weigh it on a kitchen scale, or trip over it in the hallway. It is a physical field, a region where magnetic forces act on moving charges, currents, and magnetic materials. Around Earth, that field gently nudges compass needles. Around the sun, magnetic fields guide plasma, shape sunspots, twist loops of hot gas, and drive solar eruptions. Around a pulsar, magnetic fields channel charged particles and help create beams of radiation. Around a magnetar, the field becomes so intense that it is no longer a background feature. It becomes the dominant environment. It is the weather, the landscape, the engine, and the source of tension all at once. Close to a magnetar, atoms would not behave the way atoms behave here. In everyday life, atoms are held together by electromagnetic forces. Electrons occupy regions around the nucleus, and chemistry depends on those electron arrangements. The shape of electron clouds, the spacing of energy levels, the way atoms bond to other atoms, all of that belongs to the calm electromagnetic world we live in. But a magnetar's field can distort atoms into long, thin shapes aligned with a magnetic field. The usual spherical or cloud-like picture becomes stretched. Chemistry, at least chemistry as we know it, would not survive in the ordinary way. It is not that the magnetar politely changes the rules, it overwhelms the conditions under which the rules usually express themselves. That is what people mean when they say a magnetar's magnetic field could tear atoms apart or deform them beyond recognition. The exact effect depends on distance, field strength, and the kind of matter involved. But the basic idea is that close enough to the magnetar, electromagnetic forces from the star's field are stronger than the forces keeping atoms in familiar arrangements. Your body, a notebook, a spacecraft, a bowl of soup, all of them depend on atoms behaving normally. Near a magnetar, normal is not on the menu. The field would interfere with the structure of matter before you had time to develop a thoughtful opinion about it. This does not mean magnetars are dangerous to us from where they are. That is an important bedtime clarification. The known magnetars are very far away, scattered across the galaxy or beyond, and their magnetic fields weaken rapidly with distance. A magnetar on the far side of the Milky Way is not reaching into your bedroom and pulling the coins from your pocket. The field is extreme close to the star, but space is wide and distance is generous. By the time its radiation or magnetic influence is relevant to Earth, we're usually talking about detectable signals, not nearby danger. This is one of the reasons astronomy is such a comfortable way to learn about terrifying things. We can study them through light and particles while remaining safely under a blanket. Near the magnetar itself, though, the magnetic field shapes almost everything. The star's surface is not like a planet's surface, but a crust of dense matter under immense pressure. The magnetic field threads through this crust and extends into the space around the star. If the field were perfectly calm and settled, the magnetar might simply cool and fade more quietly. But magnetar fields are not thought to be perfectly calm. They can be twisted, wound, and stressed. Parts of the field inside the star may slowly shift over time as the star cools and evolves. These changes can push on the crust from below or twist the magnetosphere above. The crust, though incredibly strong, is not infinitely flexible. Stress can build. This is where the magnetic field begins to act like stored energy. A magnetar is not powered by ordinary fusion, because that ended with the life of the original massive star. It is not mainly powered by rotation in the same way many ordinary pulsars are, although rotation still matters. The magnetar's unusual X-ray brightness and bursts are mostly explained by the decay and rearrangement of its magnetic field. That field contains energy. When the field changes, some of that energy can be released as heat, particle acceleration, X-rays, gamma rays, or motion in the crust. A magnetar is not just magnetic in the way a bar magnet is magnetic. It is magnetic in a way that gives it a long, restless afterlife. Imagine bending a metal ruler very slightly and holding it there. The ruler contains stored elastic energy. If you let go, it springs back. Now imagine that the ruler is a star's crust. The bending is caused by magnetic forces, and the release can produce high-energy radiation across thousands or tens of thousands of light years. The comparison is not exact, because neutron star crust is not office stationary, and it would be unwise to put either in your mouth, but it helps. The magnetic field can stress the star. The star can resist for a while, then something shifts, cracks, or rearranges, and energy comes out above the surface. The magnetosphere is also important. A magnetosphere is the region dominated by an object's magnetic field. Earth has one. Jupiter has a huge one. The Sun has magnetic influence extending through the solar system as part of the heliosphere. A magnetar's magnetosphere is much smaller in physical extent compared with those planetary and solar structures, but much more intense near the star. Charged particles move along magnetic field lines. Electric currents may flow through the twisted field. Radiation can scatter through this environment, changing its spectrum before it reaches us. When astronomers study a magnetar's X-rays, they're not always seeing a simple hot surface. They may be seeing light that has traveled through a complicated magnetic region filled with charged particles and twisted fields. This is one reason magnetar observations can be difficult to interpret. The magnetic field is invisible, but it changes what the visible and invisible radiation looks like. Astronomers have to infer the field from spin-down measurements, burst behavior, spectra, timing, polarization, and theoretical models. They're not taking a photograph of magnetic field lines. They're reading the effects of those lines on radiation and matter. It is a bit like trying to understand the shape of the wind by watching curtains move in a dark room. You cannot see the wind directly, but if you watch carefully, you can learn how it flows. There is also a strange quantum side to magnetar fields. In ordinary situations, empty space behaves as though it is empty enough. But in extremely strong magnetic fields, quantum electrodynamics predicts that the vacuum itself can behave in unusual ways. One important effect is called vacuum birefringence, where the vacuum acts a little like a special optical material, changing the polarization of light passing through a strong magnetic field. This is not kitchen table physics. It is one of those ideas that makes the vacuum sound less like nothing and more like a very quiet something with opinions under pressure. Magnetars offer a natural place to test such ideas because their fields are strong enough to bring these subtle effects into astrophysical relevance. Even light does not pass through the region around a magnetar as though nothing unusual is happening. X-rays leaving the surface may be polarized, scattered, or shifted by the magnetosphere. High-energy photons may interact with the intense field in ways that would be negligible almost anywhere else. In ordinary space, light mostly travels freely unless it meets matter or gravity. Near a magnetar, the magnetic field itself becomes part of the light's journey. The field is not a wall, not a cloud, not a solid obstacle, but it changes the rules of the neighborhood. The magnetic field also affects the star's cooling. Young neutron stars are hot, and they cool by releasing neutrinos and later photons from their surfaces. In magnetars, magnetic field decay can add heat, especially in the crust. That heat can make magnetars brighter in X-rays than ordinary cooling neutron stars of similar age. So when astronomers see a neutron star shining more strongly in X-rays than its rotation alone can explain, they may suspect magnetic energy is involved. This was one of the clues that led to the magnetar model. Some sources, once called anomalous X-ray pulsars, were strange because they emitted too much X-ray energy to be explained by the usual mechanisms. The anomaly made sense when the magnetic field became the power source. The word field can make all of this sound smooth and continuous, but the reality can be lumpy, twisted, and changing. Magnetic field lines are often drawn as neat loops in diagrams, which is helpful for learning, but nature is rarely that tidy. A magnetar's field may include a large-scale dipole component, like a north and south magnetic pole, but also smaller-scale multipoles, tangled structures, and internal components much stronger than what is measured at the surface. The simple field we infer from spin-down may not tell the whole story. Some magnetars may have relatively modest external dipole fields while still hiding stronger internal or local surface fields. This matters because bursts and heating may depend on those local stresses. The magnetar may look quieter from far away than it feels inside. This gives magnetars a slightly deceptive quality. You might measure the rotation, estimate the dipole field, and think you know the object. Then it bursts. Then its spectrum changes. Then its pulse profile shifts. The star has more going on than the simplest model shows. That is not a failure of science. That is science doing its ordinary work. A simple model is built first, then nature taps it on the shoulder and says, kindly or not, there is more. Magnetars have been tapping astronomers on the shoulder for decades. One especially useful fact is that magnetars rotate relatively slowly compared with many young pulsars. Their periods are often a few seconds. The strong magnetic field acts as a brake, causing them to spin down over time. As they slow, astronomers can measure the rate of change and estimate the strength of the external dipole field. It is an elegant method. The field cannot be seen directly, but its braking effect is visible in the timing. A neutron star's rotation is a clock, and magnetism is the hand slowing it. Of course, magnetars are not perfect clocks. Glitches, timing noise, outbursts, and changes in the magnetosphere can complicate the measurements. Even their clocks have a slightly dramatic temperament. If we bring the scale back down to human intuition, one often quoted example is that a magnetar placed far closer to Earth than any real magnetar is, perhaps tens of thousands of miles away, would erase magnetic data from credit cards across the planet. That image is memorable because it uses something ordinary and slightly annoying. It does not fully capture the horror of being close to such an object, but it gives the mind a small handle. Of course, long before you worried about your bank card, you would have other problems, including radiation, gravity, tides, and the fact that the magnetar itself is a city-sized stellar corpse with a surface you should not attempt to visit. Still, the credit card image works as a reminder that magnetic fields can affect information and matter, even without physical contact. Close enough, the magnetic field would also create enormous tidal and electromagnetic effects across a body. Different parts of an object would experience different conditions. Charged particles would be forced into paths along field lines. Materials would be ionized. Molecular bonds would lose their ordinary meaning. It is not a place for chemistry, biology, or cheerful exploration. A magnetar does not need to touch you to destroy you. Its field, radiation, and gravity would do all the greeting required. Fortunately, again, the real magnetars we know are separated from us by great distances. The universe can be studied without becoming a participant in its worst customer service experiences. What is remarkable is that the magnetic field is both terrifying and informative because it is so extreme. It allows scientists to study physics that cannot be reached on Earth. Magnetars are laboratories for strong field electrodynamics, dense matter, plasma physics, nuclear physics, and relativity. Their bursts tell us about crustal stresses and magnetospheric changes. Their steady X-ray emission reveals heating and cooling. Their spin down tells us about external fields. Their spectra may reveal particles, scattering, and magnetic structures. Their rare giant flares show how much energy can be stored and released in a compact star's magnetic environment. A magnetar is dangerous up close, but from far away it becomes a message. There is something almost funny in a quiet way about the fact that magnetism, the same basic phenomenon that helps a compass needle turn north, can also be responsible for some of the most violent outbursts in the galaxy. It is not a different universe using different rules. It is the same universe with the same forces under different conditions. A fridge magnet and a magnetar are not similar in any practical sense, but they belong to the same broad family of physical behavior. One holds up a holiday photo, the other can release gamma rays across interstellar space. Physics has range, so when we say the magnetic field is strong enough to tear atoms apart, we are really saying that the environment near a magnetar lies outside the ordinary conditions under which matter becomes familiar. Atoms stretch, chemistry fails, light changes, charged particles are trapped and guided. The crust is stressed, the star is heated, rotational energy drains away, bursts become possible. The magnetic field is not an accessory, it is the defining feature, the force that turns a neutron star into a magnetar and gives the object its restless, high-energy life after death. At first, the phrase starquake sounds almost too dramatic, as if astronomy borrowed it from a disaster movie and decided not to give it back. We know what an earthquake is, at least in the ordinary earthly way. The ground shifts, faults slip, buildings tremble. Somewhere, a shelf full of cups begins to regret its design. But a starquake is not a quake in rock, soil, or stone. It happens on an object whose surface is made from matter compressed beyond anything in everyday life, wrapped in a magnetic field so strong that the field and the crust are locked together in a restless relationship. On Earth, the ground moves because tectonic plates grind, pull, and press against one another. On a magnetar, the crust may shift because the magnetic field beneath and above it is changing, building stress and tugging at one of the strongest solid surfaces in the universe. A magnetar's crust is not thick in the way Earth's crust is thick. Earth has a rocky crust that can be tens of kilometers deep under continents and thinner beneath oceans. Below it sits mantle, then outer core, then inner core, each layer familiar enough to be placed in school diagrams, usually with colors that look rather like a slice of boiled sweet. A neutron star's crust is different in almost every way. The whole star may be only about the size of a city, and its crust is a relatively thin outer layer, perhaps around a kilometer or so thick, depending on the star's mass, radius, and the dense matter physics we're still trying to understand. Thin, however, does not mean fragile. A sheet of paper is thin. A neutron star crust is thin in the way a bank vault door would be thin if the bank vault were made from atomic nuclei packed under enormous pressure near the surface. The crust contains atomic nuclei and electrons arranged in a dense lattice. That sentence sounds tidy, but it is worth slowing down over it. In ordinary solids, atoms sit in patterns and electrons help determine how the material behaves. In the outer crust of a neutron star, matter is squeezed so tightly that the nuclei are packed in ways no ordinary mineral can imitate. Deeper down, the pressure becomes more intense. Nuclei become richer in neutrons. Eventually, neutrons begin to drip out of nuclei, forming a kind of neutron fluid alongside the nuclear lattice. Deeper still, near the base of the crust, scientists expect matter may form strange shapes, sometimes nicknamed nuclear pasta. The name is charming, almost too charming, as if the universe decided that after making one of the harshest materials possible, it should label the shapes after spaghetti and lasagna to make everyone feel better. Nuclear pasta is not food, which is probably clear but still worth saying for safety. It is a theoretical phase of dense nuclear matter where atomic nuclei under immense pressure may stretch and arrange into rods, slabs, tubes, and other shapes. The names come from the resemblance in simulations, spaghetti, lasagna, and similar kitchen-friendly terms. But the substance itself may be incredibly strong, possibly among the strongest materials in the universe. Some studies suggest that breaking this kind of neutron star material would require forces vastly beyond those needed to break steel. Steel, to us, is a symbol of strength. We build bridges with it, we make tools with it, we trust it to hold skyscrapers upright and ships together. A neutron star crust treats steel the way steel treats whipped cream, which is perhaps not a standard engineering comparison, but it gives the general direction. That strength matters because a magnetar's crust has to resist magnetic stress. The magnetic field does not sit politely outside the star like a decorative halo. It threads through the crust and the interior. It pushes and pulls on charged particles and currents. It can shift over time as the star cools and its internal magnetic structure evolves. The field may want to rearrange itself into a lower energy shape, but the crust can resist, so stress builds. The crust holds and holds and holds until some part of it may no longer be able to adjust smoothly. Then something gives. On Earth, earthquakes happen when stress in rock is released along faults. Plates move slowly, but rock does not always slide continuously. It sticks, stores strain, and then slips suddenly. That sudden slip sends seismic waves through the planet. On a magnetar, the comparison is helpful, but only if we remember its limits. There are no oceans, no mountains, no tectonic plates in the familiar sense. The crust is made from dense nuclear matter. The stress comes largely from magnetic forces, not plate tectonics. The waves that move through the star are not traveling through granite or basalt, but through a crust and interior shaped by gravity, nuclear physics, and magnetic fields. Still, the idea of stored stress and sudden release is useful. A starquake is the magnetized version of a locked system finally shifting. The release may begin with a fracture, or perhaps with plastic deformation where the crust flows or yields rather than snapping cleanly like a brittle plate. Scientists still debate exactly how magnetar crusts fail. The word quake suggests cracking, but under such immense pressure, matter may not behave like ordinary brittle rock. It may bend, creep, shear, or deform in complex ways. Some models emphasize crust breaking. Others suggest that magnetospheric reconnection, a sudden rearrangement of magnetic field lines outside the star, may play the leading role in bursts, with the crust helping drive or respond to the change. Nature may use more than one method. Magnetars are not obligated to keep their paperwork simple. Whatever the precise trigger, the connection between crust and magnetic field is central. If the crust shifts, it can shake the magnetic field. If the magnetic field rearranges, it can shake the crust. The two are tied together. Imagine holding a tablecloth with heavy dishes on it, then twisting one corner very slowly. For a while, everything might resist. A plate may slide a little, a cup may rattle. Then one object moves suddenly, and the whole arrangement changes. This is a very mild and domestic comparison, and a magnetar would be offended by the scale, but it helps. The crust and magnetic field form a stressed system. A small shift can have large consequences because the magnetic energy available is enormous. When a starquake happens, it may send seismic vibrations through the neutron star. These are not gentle ripples in a pond. They are oscillations in a compact object with gravity billions of times stronger than Earth's, density near nuclear values, and a magnetic field strong enough to dominate the star's outer behavior. Some vibrations may be torsional, meaning parts of the crust twist back and forth. If you imagine holding one end of a rubber eraser and gently twisting the other, you have a tiny hint of the motion, though a rubber eraser is not under neutron star gravity and usually does not emit gamma rays afterward. These torsional oscillations can, in principle, tell scientists about the crust's strength, thickness, and composition. This is where magnetars become more than spectacular objects. They become instruments. When a magnetar flares and its crust vibrates, astronomers may detect quasi-periodic oscillations, often shortened to QPOs, in the X-ray or gamma-ray signal. These are patterns in the brightness that repeat at certain frequencies for a time. If those frequencies are linked to seismic vibrations of the star, then they can reveal something about the star's interior. It is a little like learning about Earth's interior from earthquake waves. Seismologists study how waves travel through our planet to infer layers we cannot visit directly. In magnetars, astrophysicists hope to use starquake vibrations to do something similar for neutron stars. This field is sometimes called astroseismology, and it is one of those words that sounds complicated until you realize it simply means listening to stars shake. The listening is not done with ears, of course. No sound travels through the vacuum of space in the way sound travels through air. Astronomers listen with detectors. By measuring changes in high-energy light, X-rays and gamma rays carry information from the magnetar. Telescopes in space. Earth's atmosphere blocks much of this radiation, which is very nice of it from a biological standpoint, but inconvenient for astronomers are needed. Instruments like NASA's Fermi Gamma Ray Space Telescope can detect high-energy bursts and record their timing. In some magnetar events, careful analysis has revealed patterns that may be connected to seismic waves rippling through the star. It is a strange form of listening, catching gamma rays from a dead star and finding the rhythm of its crust. The 2004 giant flare from SGR 186-2000 became especially important in this context. That event was extraordinarily bright, and after the initial spike, the decaying signal showed oscillations at certain frequencies. Scientists interpreted some of these as possible vibrations in the magnetar, linked to starquake activity. Similar ideas have been explored for other magnetar flares as well. These signals are not always easy to interpret. A magnetar's emission comes from a complicated environment, including the crust, the magnetosphere, the magnetic field, and relativistic particles. Still, the possibility is powerful. A sudden flare may briefly turn a magnetar into a ringing bell, and the tones in that bell may tell us what the star is made of. This is not just curiosity for curiosity's sake, though curiosity is already a perfectly respectable reason. Neutron star interiors are one of the great puzzles in physics. We know they are dense, but we do not know exactly how matter behaves at the highest densities inside them. Are the cores mainly neutrons with a small fraction of protons and electrons? Do exotic particles appear? Are there hyperons, pion condensates, or even quark matter in some stars? These are hard questions because the interiors are hidden, and the matter inside them exists at pressures far beyond ordinary experiments. Starquakes and oscillations offer one way to test models. The crust's response depends on its composition and strength. The frequencies of vibrations depend on the star's structure. So a flare is not only a flash, it is a clue. It is worth pausing over the strength of the crust again, because it gives the starquake idea its tension. If the crust were weak, stress would not build in the same way. It would simply adjust, flow, and release energy gently. But neutron star crust is expected to be incredibly strong. It can store strain. It can resist deformation. That means when it finally shifts, the release can be sudden and powerful. There is a quiet lesson there, though we do not need to make it too philosophical. Strong things can store enormous tension. When they change, the change can be dramatic. A magnetar's crust is also under immense gravity. Any mountain on a neutron star would be tiny by Earth standards, because gravity pulls everything flat so strongly. A bump only a few centimeters high could be significant. The surface is not smooth in the way a polished marble is smooth, but the scale of possible features is crushed by gravity. The crust is held down by the weight of the star's own compact mass. This makes the idea of it cracking even stranger. You're not imagining a dry desert floor splitting under sunlight. You're imagining dense nuclear matter pressed by immense gravity, stressed by magnetic forces, and shifting under conditions so extreme that even the word surface feels almost too casual. When the crust moves, energy can be injected into the magnetosphere. Magnetic field lines may twist or reconnect. Charged particles can be accelerated. Radiation can be released in bursts. Many magnetar bursts are short, lasting fractions of a second or a few seconds. They can happen in storms, with many bursts occurring over a short period. Some are modest by magnetar standards. Others are giant flares, rare events with enormous energy. The small bursts may be like little adjustments, the star clearing its throat in X-rays. The giant flares are more like the star slamming the cosmic table, though again, not a table one should sit near. One careful point is that not every burst has to be caused by a literal crust crack. Magnetar activity may involve both internal and external triggers. The magnetosphere can store twisted magnetic energy and release it through reconnection, somewhat analogous to solar flares. The crust can twist the field from below, or the magnetosphere can become unstable on its own after being gradually stressed. In some cases, the observed burst may mostly reflect activity outside the star, even if the underlying energy comes from internal magnetic evolution. The truth may be a partnership. The crust, the interior, and the magnetosphere are all connected parts of one magnetic system. That connected system can also produce glitches. In neutron stars, a glitch is a sudden change in rotation rate, often a small spin-up. Glitches are observed in ordinary pulsars and in magnetars. They may involve the star's interior superfluid, where neutrons move with almost no friction, interacting with the crust. In magnetars, glitches can sometimes be associated with bursts or outbursts, suggesting that the internal dynamics, crustal stress, and magnetic activity may be linked. This is another place where the dead star label becomes misleading. A magnetar is not a simple solid ball spinning in space. It has layers, fluids, fields, stresses, and timing irregularities. It is a compact object with a complicated inner life, which, to be fair, many of us can relate to on a quiet evening. The idea of a crust harder than steel does not mean the crust is indestructible. Strength is about how much stress a material can withstand before changing or breaking. Given enough stress, even the strongest material yields. In a magnetar, the magnetic field can provide that stress. The field may evolve slowly over years, decades, centuries, or longer. The crust responds, sometimes gradually, sometimes suddenly. The star's surface can heat unevenly. Hot spots may appear, affecting the pulse profile as the star rotates. After an outburst, the X-ray brightness may decay over months or years as the crust cools and the magnetosphere relaxes. Astronomers watch these changes carefully because the cooling pattern can reveal how heat moves through the crust. This is a wonderfully indirect kind of science. A magnetar flares. A telescope records X-rays. Astronomers measure how the brightness fades. The fading tells them something about heat deposited in the crust. That heat tells them something about the depth and nature of the event. The event tells them something about magnetic stress. The magnetic stress tells them something about the star's field and interior. The object is far away, too small to image as a surface, too dense to sample, too dangerous to approach. And yet, patient observation turns its outbursts into information. Space often gives us locked doors and then slips the key under the light curve. The term starquake also helps us imagine the scale of energy, but it should not make us think only of shaking matter. In a magnetar, the quake and the flare may be parts of the same episode. A crustal shift can launch alpha waves, waves traveling along magnetic field lines through magnetized plasma. These waves can carry energy into the magnetosphere. There, energy can become radiation. The details are still modeled and debated, but the general idea is that a mechanical or magnetic disturbance does not stay neatly in one form. It moves through the star field system, changing from stress to motion to particle acceleration to X-rays and gamma rays. A magnetar is very good at converting stored magnetic tension into signals we can detect from far away. These signals appear as sudden changes in brightness. A quiet source brightens, a burst arrives, a storm of bursts flickers. Then the object settles again, though perhaps not to exactly the same state as before. Its pulse shape may be different. Its X-ray spectrum may change. Its spin-down rate may shift because the magnetosphere has been reconfigured. Astronomers do not just record the explosion and move on. They watch the aftermath. The recovery is part of the event. A magnetar after an outburst is like a room after a loud noise. Things are still, but not quite arranged as they were. There is a calming aspect in the timescales. Even though the physics is violent, the stress may build slowly. The burst may happen quickly. The cooling may take months. The star may remain quiet for years before surprising everyone again. We see only pieces of the full life. A magnetar has a long internal history we infer from brief episodes. This makes each burst valuable. There are not many known magnetars, and giant flares are rare. When one occurs, telescopes across the world and in space pay attention. The star has spoken, if speaking can mean releasing high-energy radiation after a crustal disturbance in a city-sized dead star. Astronomy stretches language in interesting ways. A person near a magnetar would not experience a starquake as a rumble underfoot, because there is no safe foot, no safe ground, and no safe person. The gravity and magnetic field would already be fatal long before any scenic observation could take place. But from Earth, a starquake becomes a remote tremor in data. We do not feel the ground move. We see a detector count jump. We see a light curve flicker. We see frequencies hidden in the signal. It is one of the universe's strangest translations. A crack or twist in a stellar crust becomes a pattern on a graph, and the graph becomes a way to understand matter at its limits. So a starquake is not just an earthquake with a bigger name. It is a release of stress in an object where the crust may be stronger than steel, where the magnetic field can be strong enough to deform atoms, where gravity crushes the surface into a compact shell, and where even a small movement can send energy into space. It shows us that the solid part of a neutron star is not passive. It participates in the magnetar's life. It holds stress, transmits waves, heats, cracks, shifts, and perhaps rings. The crust is a thin shell by neutron star standards, but it is one of the key places where the magnetar's hidden magnetic life becomes visible. A magnetar can spend long stretches of time seeming almost quiet, at least from our distant point of view. It may pulse in X-rays. It may glow with the leftover heat of a young neutron star. It may slowly spin down as its magnetic field drags against the surrounding space. Astronomers can measure it, watch it, model it, and begin to feel very cautiously that they understand its mood. Then the magnetar reminds everyone that a dead star with a magnetic field like that is not a settled thing. It flares. A giant flare is one of the rarest and most dramatic ways a magnetar can announce itself. This is not the steady beam of a pulsar sweeping past Earth like a lighthouse. It is not the slow brightening of a star or the ordinary flicker of a distant source. It is sudden, high energy, and brief in its most intense moment. The first spike may last only a fraction of a second, so fast that if you blinked at the wrong moment, in human terms, you would miss the main event. But space telescopes do not blink in quite the same way, and when they catch one of these flares, the data can be startling. In a tiny slice of time, a magnetar can release more energy than the sun emits over many thousands of years. The universe, which is usually very patient, sometimes does things faster than a kettle can click off. The word flare might make it sound like a solar flare, and that comparison is useful up to a point. The sun also has magnetic fields. Its surface and atmosphere are threaded by loops and arcs of magnetism. When those fields twist and reconnect, energy can be released, heating plasma and sending radiation and particles into space. Solar flares can affect satellites, radio communication, and power systems on Earth. They are important, powerful events, and we take them seriously. A magnetar giant flare, however, comes from a much smaller object with a much stronger field. It is as if the magnetic idea behind a solar flare has been compressed into a city-sized neutron star and given a far more extreme energy budget. Scientists often describe magnetar flares as connected to sudden rearrangements of the magnetic field. The field may be twisted, storing energy in the magnetosphere and in the star itself. A starquake or crustal shift may disturb the magnetic structure. Field lines may reconnect. A trapped fireball of hot plasma and radiation may form close to the star. The exact details are still studied, and different flares may not all work in exactly the same way, but the broad picture is clear enough. Magnetic energy that has been stored in a stressed system is suddenly released. The result is a blast of X-rays and gamma rays that can race across the galaxy at the speed of light. Gamma rays are the highest energy form of light. They are not visible to human eyes. You cannot stand outside and see gamma rays sweeping through the sky like a blue-white flash. That is probably good, because if your eyes were detecting gamma rays directly, your evening would already have taken a troubling turn. Space telescopes detect them with specialized instruments. These instruments count particles, measure energies, and record arrival times. A giant flare may hit several spacecraft at once, sometimes so strongly that detectors saturate. Instruments built to watch high-energy events may suddenly be overwhelmed by a burst from a source they were not necessarily staring at directly. A magnetar does not always make an appointment with a telescope. The basic shape of a giant flare often has two parts. First comes the initial spike, extremely bright and extremely short. This is the explosive release, the sudden opening of the magnetic pressure valve. Then comes a longer tail, lasting minutes in some famous cases, fading and pulsing as the magnetar rotates. That tail can be modulated by the spin of the neutron star, because the hot region or trapped fireball is not seen equally from every angle. As the magnetar turns, the emission rises and falls. It is like watching the afterglow of a catastrophe sweep around with the star's rotation, except the star is a dense remnant and the afterglow is high-energy radiation from a magnetically trapped environment. Astronomy has a way of making the word afterglow carry more weight than it does around a campfire. Only a few true giant flares have been observed from magnetars in and near our galaxy. One of the earliest was linked to SGR 05-2066 in the Large Magellanic Cloud in 1979. Another major event came from SGR 1900+14 in 1998. Then came the extraordinary flare from SGR 1806-20 on December 27, 2004. That one became famous because of its sheer intensity. The source was on the far side of the Milky Way, roughly tens of thousands of light years away. Yet the flare was still strong enough to affect Earth's upper atmosphere and saturate instruments. The flash had crossed an enormous stretch of space before reaching us, traveling for about 50,000 years. When it finally arrived, the energy passed over Earth in an instant, touching detectors, disturbing the ionosphere, and reminding astronomers that even the far side of the galaxy is not always far enough to make the universe feel tame. Think about that timing for a moment. When the flare left SGR 1806-20, humans on Earth were living in the late Stone Age. No cities, no telescopes, no satellites, no written astronomy, no one waiting with an instrument and a neat observation log. The gamma rays traveled while glaciers shifted, while human cultures rose, changed, and spread, while languages appeared and vanished, while generations lived beneath skies that had no idea what was on the way. Then, on one day in 2004, the signal arrived. Space telescopes recorded it. Scientists traced it back to a magnetar. A burst that began before civilization reached us through machines built only recently enough to catch it. That is one of the quieter wonders hidden inside high-energy astronomy. We do not just observe violent events, we observe ancient violence arriving late. The 2004 event was so bright that if you judged only by the gamma-ray sky, it briefly became one of the most intense signals ever seen from beyond the solar system. It was not close in ordinary terms. It was not even in our neighborhood of the galaxy, and yet its effect on instruments and Earth's ionosphere was measurable. The ionosphere is a layer of Earth's upper atmosphere where solar ultraviolet light and X-rays ionize atoms and molecules, creating free electrons and ions. It is involved in radio propagation and is sensitive to high-energy radiation. Usually the sun is the main actor in ionospheric changes. On that day, a magnetar far across the galaxy briefly joined the conversation, which is quite rude for an object only about the size of a city. When people say a giant flare can shake space across the galaxy, they're usually speaking in a poetic but understandable way. The flare does not shake space like a hand shaking a blanket. It sends a wave of electromagnetic radiation outward, and that radiation can shake instruments, ionize upper atmospheres, and light up detectors across huge distances. The event also may eject material or disturb the surrounding environment, producing radio afterglows that astronomers can track. The flare is not a sound wave moving through space, because space is mostly vacuum and sound needs a medium. It is light, high-energy light, racing outward in all directions, or perhaps partly beamed, carrying information and energy from the magnetar's sudden magnetic rearrangement. Still, from the point of view of observatories scattered across the solar system, it can feel as if space itself received a sharp tap. The source of the energy is magnetic. That is the important thread running through everything. The magnetar's rotation contains energy, and its heat contains energy. But the giant flare is thought to draw primarily from magnetic energy stored in and around the star. Magnetic field
really
lines may be twisted by motion of the crust. The magnetosphere may become unstable. A crustal fracture may launch waves and alter the external field. Reconnection may release energy rapidly, somewhat like what happens in solar flares, though at vastly greater magnetic intensity. A fraction of the magnetar's magnetic reservoir suddenly becomes radiation, particle motion, and perhaps ejected material. The conversion is brief, violent, and efficient enough to be seen across enormous distances. The trapped fireball idea is one of the more vivid parts of the model. After the initial spike, some energy may remain confined close to the magnetar by its strong magnetic field. This hot plasma and radiation cannot simply expand freely in all directions at once because the magnetic field dominates the motion of charged particles. Instead, the field holds part of the energy near the star, and as the fireball cools, it emits X-rays and gamma rays over a longer tail. Because the magnetar is rotating, that tail can pulse. The observed signal carries the period of the star's spin, allowing astronomers to connect the flare not just to an explosion, but to the rotating object at its center. The flare's afterlife is stamped with the magnetar's rhythm. That rhythm matters. It tells us that the source is compact and rotating. It lets astronomers study how the emission region changes as the flare fades. In some giant flares, the pulse profile changes after the main spike, suggesting that the magnetosphere has been rearranged. The star is not exactly the same before and after. A major release of magnetic energy can change the currents around it, the shape of the field, the pattern of hot spots, and the way radiation escapes. A giant flare is not only an outburst, it is a restructuring. The amount of energy involved is difficult to make intuitive. One way is to compare it with the sun. The sun is steady, enormous, and luminous. It emits energy every second that dwarfs human scales completely. Yet, a magnetar giant flare can release, in a fraction of a second, energy comparable to what the sun emits over tens of thousands, or even more than 100,000 years, depending on the event and the estimate. That does not mean the magnetar is brighter than the sun in visible light in our sky. It is far away, and the energy is mainly in gamma rays and X-rays. But intrinsically, for that instant, the power is staggering. A small dead star briefly outshines normal expectation by such a margin that instruments notice from across the Milky Way. There is also a connection to gamma ray bursts, those brief flashes of gamma rays detected from random directions in the sky. Many gamma ray bursts come from extremely distant cosmic explosions, such as collapsing massive stars or merging compact objects. But some short gamma ray bursts, especially those from relatively nearby galaxies, may actually be giant flares from magnetars. If a magnetar in another galaxy releases a powerful giant flare, the initial spike might look like a short burst if the tail is too faint to detect. Astronomers therefore have to consider magnetars when classifying some high-energy transients. One object's local giant flare may be another observer's mysterious short burst. The universe enjoys disguises, especially when the lighting is poor. The rarity of giant flares makes them both exciting and frustrating. Astronomers cannot simply schedule one for next Thursday at a convenient time after lunch. They wait. Instruments monitor the high-energy sky. Some magnetars produce smaller bursts more often, but the truly giant events are rare. When one occurs, the data may arrive from multiple spacecraft with different sensitivities, viewing angles, and saturation problems. The initial spike may be too intense for some detectors to measure cleanly. The tail may be easier to study. The aftermath in radio or X-rays may unfold over days, weeks, or months. Scientists then piece together the event from many instruments. a little like reconstructing a thunderstorm from rain gauges, lightning cameras, broken umbrellas, and one very startled person at a bus stop. The 2004 SGR 18062 flare had an aftermath that could be studied in radio light. Observations found an expanding radio nebula associated with material ejected during the event. This is remarkable because it suggests that the flare did not only release radiation, it also launched matter outward at high speeds. That matter interacted with the surrounding environment, producing radio emission that changed over time. So, the giant flare had a body as well as a flash. It disturbed the space around the magnetar, and astronomers could watch the disturbance expand. For an object so small and distant, that is an impressive way to leave fingerprints. The phrase giant flare may hide a range of events. There are ordinary short magnetar bursts, intermediate flares, and rare giant flares. The boundaries are not always perfectly clean, but the giant ones stand out because of their enormous energy and distinctive structure. They are the extreme end of magnetar activity, the everyday life of a magnetar, if everyday is not too cozy a word for a neutron star, may involve persistent X-ray emission and occasional bursts. A giant flare is the rare moment when the magnetic system releases a major portion of stored stress at once. It is the difference between a floorboard creaking at night and the whole attic deciding to rearrange itself. One question scientists ask is what determines when a giant flare happens? The magnetic field evolves over time. Stress builds in the crust and magnetosphere. Some threshold may be crossed, but the exact trigger is difficult to predict. Unlike ordinary stars, where some changes can be modeled over long timescales, magnetar flares depend on the detailed magnetic structure of a compact object we cannot see directly. We can observe signs of increasing activity before some flares, such as changes in persistent emission or spin-down behavior. But there is no simple forecast system. There is no magnetar weather app saying high chance of gamma rays after midnight. Astronomers rely on monitoring, rapid alerts, and follow-up observations. The consequences depend very strongly on distance. A giant flare from a magnetar thousands or tens of thousands of light-years away may be a scientific gift, not a danger. It can disturb the upper atmosphere and affect detectors, but it does not harm life on Earth. A similar flare much closer, within a few light-years, could be much more serious, potentially damaging the atmosphere. Fortunately, there are no known magnetars close enough to pose that kind of threat. The dangerous neighborhood is empty, at least as far as we know, which is one of the more comforting sentences in high-energy astrophysics. The galaxy is full of extreme things, but distance is a powerful shield. It is worth remembering that these flares are not explosions destroying the magnetar. After a giant flare, the magnetar remains. It may be altered. Its magnetosphere may be changed. Its persistent emission may decay. Its pulse shape may shift, but the star is still there, still rotating, still magnetic, still capable of future activity. A giant flare is enormous, but it is not the end of the object. The magnetar's magnetic energy reservoir is large enough that even a giant flare is only part of its story. This is another strange scale contrast. From our point of view, the flare is one of the brightest high-energy events ever observed. From the magnetar's point of view, if it had one, it may be a major adjustment, but not a final act. The light from a giant flare travels outward long after the magnetar itself has moved on to whatever state follows the event. That radiation crosses interstellar dust, passes between stars, spreads through the galaxy, and eventually reaches planets, spacecraft, detectors, and perhaps other worlds with no instruments to notice it. Most of the wavefront continues beyond us, out into intergalactic space. The flare becomes a growing sphere of information expanding at the speed of light. Somewhere far away, long after the star's crust shifted, the signal is still traveling. The magnetar's moment becomes a moving shell in the dark. There is a quiet beauty in the fact that we can study such a moment at all. The flare is brief, the source is tiny, the distance is vast. The radiation is invisible to our eyes, and yet through a network of instruments, satellites, timing systems, and careful analysis, human beings can say, a magnetar shifted. Its magnetic field released energy. The burst crossed the galaxy. Earth's upper atmosphere responded. The tail pulsed with the star's rotation. That is a remarkable chain of knowing. It begins with a dead star cracking or reconnecting in the dark, and ends with scientists reading a light curve on Earth. So a giant flare is not simply a bigger burst. It is a window into the Magnetar's magnetic architecture. It shows that the field can store astonishing energy. It shows that the crust and magnetosphere can change suddenly. It shows that a neutron star only about the size of a city can affect environments across galactic distances. It also shows that the calm night sky is full of delayed arrivals. A flash that left a magnetar before recorded history can arrive in the modern era, quietly entering our instruments while the rest of the world goes about making dinner, answering emails, or wondering where the charging cable went. And after we understand that these flares can cross the galaxy, the next natural question becomes more personal and perhaps a little less relaxing, though we will take it slowly. What would happen if something were not far away from a magnetar? What if a spacecraft, a planet, or a very unfortunate traveler came too close to that magnetic field, that gravity, and that high-energy radiation? The safest way to visit a magnetar is not to visit one at all. This is a useful rule, and unlike many useful rules, it does not come with much of a gray area. There are some places in the universe that are dangerous because they are hot, some because they are cold, some because they are full of radiation, some because gravity is not being friendly, and some because the local magnetic field has become so unreasonable that ordinary matter would like to file a complaint. A magnetar manages to combine several of these problems into one compact object. It is small enough to hide in the darkness between stars, yet extreme enough that getting close to it would not be an adventure so much as a very brief physics lesson with no surviving notes. Still, thought experiments are one of the few ways we can approach something like this. We do not send a spacecraft. We do not plan a landing. We do not ask whether there is parking nearby. Instead, we imagine moving inward from a safe distance, step by careful step, and watch which dangers appear first. This is not because anyone should go there, but because asking what would happen nearby helps us understand what a magnetar really is. A distant object can become just a name, a point in a catalog, a strange source of X-rays. But when we imagine the environment around it, the name becomes a place, or at least something like a place, though not one with gift shops. Far away from the magnetar, the first thing you would notice is not the magnetic field directly. Space is enormous, and magnetic fields weaken rapidly with distance. From many light years away, a magnetar is not reaching out like a cosmic vacuum cleaner, pulling on your keys or rearranging the cutlery drawer. This is worth saying clearly because magnetars sound so dangerous that it is easy to imagine them as threats from anywhere in the galaxy. They are not. The known magnetars are safely distant. Their radiation can be detected. Their giant flares can disturb instruments or even Earth's upper atmosphere in rare cases. But their direct magnetic grip does not stretch across the Milky Way in a way that affects daily life. Your fridge magnets remain responsible for their own behavior. But if you began to travel closer, the environment would slowly become stranger. Long before you reached anything like the surface, you would be entering a region shaped by an intense magnetic field, high-energy radiation, and the gravity of a neutron star. The object itself might only be about 20 kilometers wide, perhaps the size of a city, but it may contain more mass than the sun. That means the space around it is curved strongly by gravity. Any spacecraft approaching would need to deal with an object that looks tiny but pulls with enormous force. This is one of the first traps in thinking about compact objects. Our eyes associate size with power. A mountain looks heavy, a planet looks heavier, a star looks enormous. A neutron star does not look large, but gravity does not care how large something looks. It cares about mass and distance. And a magnetar has a great deal of mass packed into a very small distance. As you came nearer, or rather, as our imaginary spacecraft came nearer while we remained comfortably elsewhere, the gravitational field would become ferocious. The difference in gravity between the near side and far side of an object would grow. This difference is called a tidal force. On Earth, tides gently raise in lower oceans because the moon's gravity pulls slightly more strongly on the near side of Earth than on the far side. Around a neutron star, the same basic effect becomes extreme. If a human body approached too closely, the tidal forces could stretch it, because the part closer to the star would be pulled much harder than the part farther away. This is sometimes called spaghettification around black holes, which is a surprisingly cheerful word for an unpleasant concept. Around a magnetar, gravity alone would already be a serious danger. even before the magnetic field had its turn. But a magnetar is not only a dense mass, it is a magnetic environment of almost absurd strength. Close to the star, the magnetic field may reach about 1,000,000 billion Gauss. It is hard to feel that number, so we need to compare it gently. Earth's magnetic field is around 1 Gauss in rough everyday comparison, though the actual value is usually less than that depending on location. A refrigerator magnet may be around 100 Gauss near its surface. Hospital MRI machines are strong enough that people handle them with great care. A magnetar is so far beyond these that the comparisons become more like stepping stones than true bridges. You cross them only to discover that the river is wider than expected. At a certain distance, the magnetar's magnetic field would begin to interfere with technology. Electronics depend on controlled movement of charges. Data storage depends on delicate magnetic or electronic states. Sensors, circuits, guidance systems, memory, and communication equipment all prefer not to be inside a cosmic magnetic storm. A spacecraft heading toward a magnetar would have its systems disrupted long before it reached the most extreme region. Instruments might saturate, circuits might fail, charged particles might be forced into destructive paths. Even if the spacecraft were built with shielding, the problem would not be like protecting a camera from rain. It would be like protecting a candle from being lowered into a blast furnace, and then asking if perhaps a small umbrella would help. For ordinary matter, the trouble grows deeper. Atoms are held together by electromagnetic forces. Electrons occupy regions around nuclei, and chemical bonds form because electrons can be shared, transferred, or arranged between atoms in stable patterns. Everything familiar depends on that. Water is water because hydrogen and oxygen bond in a certain way. Proteins fold because atoms and molecules interact according to electromagnetic rules. Metal holds its structure because atoms share electrons in a particular arrangement. A human body is a very complicated, warm, watery example of chemistry behaving under gentle conditions. Near a magnetar, those conditions vanish. A strong enough magnetic field can distort electron clouds, stretching atoms along the direction of the field. Instead of the familiar rounded or orbital-shaped distributions we use in chemistry, atoms become elongated. Their energy levels change, their bonding behavior changes. If the field is intense enough, ordinary chemistry is no longer chemistry in the way we know it. Molecules would be disrupted. Atoms would be deformed or stripped. This is what people often mean when they say a magnetar could tear atoms apart. The field would not need to grab a person like a hand. It would alter the electromagnetic structure that allows matter to be matter in the familiar sense. The body is not held together by bravery. It is held together by molecular bonds, and those bonds have limits. Radiation would add another layer. Magnetars emit X-rays steadily in many cases, and they can produce bursts of X-rays and gamma rays. Close to the source, that high-energy radiation would be overwhelming. Gamma rays can penetrate matter and ionize atoms, knocking electrons loose and damaging molecular structures. On Earth, our atmosphere protects us from much high-energy radiation from space. A spacecraft near a magnetar would not have such a helpful sky wrapped around it. Shielding against gamma rays is difficult because they are highly penetrating. You would need dense material, and even then, near enough to a magnetar, the amount of radiation could be far beyond anything practical shielding could handle. It would not be a question of wearing a better spacesuit. It would be a question of not being there. If the magnetar had recently flared, the situation would be even worse. A giant flare releases a blast of high-energy radiation and may disturb the surrounding magnetosphere close to the star. While the flare would be catastrophic for any ordinary object, the initial spike would arrive at light speed, leaving no warning in the ordinary sense. A spacecraft could not see the flare coming before the flare itself arrived because the information travels with the radiation. One moment, the magnetar is in one state. The next, the instruments are overwhelmed by an event that began at the source and crossed the local space as fast as physics allows. This is one reason giant flares are studied from far away. Distance gives the energy room to spread out, and even then, the brightest events can be powerful. The magnetosphere around the star would also be filled with charged particles moving under the control of the magnetic field. These particles can travel along field lines, radiate, scatter photons, and create a complex high-energy environment. A spacecraft moving through such a region would not be traveling through empty space in the peaceful sense. It would be entering a magnetic machine. Charged particles could batter surfaces and electronics. Induced currents could flow through conductive materials. Forces could twist and heat parts of the craft. The Magnetar's magnetic field would not simply sit around the spacecraft. It would interact with anything that could carry charge or current. And almost everything useful in a spacecraft can carry charge or current, which is wonderful near Earth and less wonderful near a magnetar. Gravity would also affect time. Around a neutron star, time runs slightly more slowly closer to the surface than it does farther away, because strong gravity warps space-time. This is not unique to magnetars. It happens around any massive object, including Earth, but it becomes much stronger near compact stars. A clock near a magnetar would tick differently compared with a clock far away. Light escaping from near the surface would lose energy, becoming gravitationally redshifted. The star's gravity bends the path of light as well, so an observer could see more of the surface than they would expect from ordinary geometry. A neutron star is so compact that its own gravity changes the view around it. The surface is not just a place, it is a place wrapped in curved space-time. If you try to orbit a magnetar at a close distance, the orbital speeds would be enormous. Stable orbits may exist outside the star, but the environment would be hostile because of radiation, magnetic fields, and possibly particle winds or bursts. You would be circling something with the mass of a star and the width of a city. The sky would not look like a peaceful science fiction panorama. The magnetar might appear small in angular size until you were dangerously close, but its effects would dominate everything. The surrounding stars would be distorted by gravitational lensing near the compact object. X-ray emission from hotspots on the surface might sweep around with the rotation. If the magnetar rotated every few seconds, its radiation could pulse like a terrible lighthouse, one you would very much prefer to observe through a detector from a safe astronomical distance. A planet near a magnetar would not be a friendly world. If it formed before the supernova, it likely would not have survived the explosion and the birth of the neutron star in any ordinary stable way. Though compact object planets do exist in some systems under special histories. If material later formed a disk and perhaps objects around a neutron star, they would live in an extreme environment around a magnetar. Radiation and magnetic activity would make habitability almost impossible. Atmospheres could be stripped or chemically altered, surfaces would be bombarded. Any life as we understand it would have no gentle environment to rely on. The phrase living near a magnetar belongs more to speculative imagination than biology. It is not the kind of place where life would look up and admire the auroras. The auroras, if they existed, would be the least of the concerns. A human body close enough to the magnetar would face several fatal processes almost at once. Radiation would ionize tissue. Tidal gravity could stretch and tear. The magnetic field could disrupt atomic and molecular structure. Charged particles would add further damage. Heat and high-energy photons would overwhelm any protective suit, but we do not need to linger on the unpleasant details. The important scientific point is that a magnetar's danger does not come from one single effect. It comes from the combination. A black hole might be known mainly for gravity. A bright massive star might be known for heat and radiation. A magnetar brings neutron star gravity, intense high-energy radiation, and the strongest magnetic fields known. It is a compact collection of reasons to keep a respectful distance. The distance at which each effect becomes serious depends on the magnetar's field strength, radiation output, flare activity, and the kind of object approaching. A credit card can lose magnetic data at a far gentler field than the field required to disrupt atoms. Human tissue can be damaged by radiation at distances where the magnetic field itself would not yet deform atoms. A spacecraft might fail because of electronics, induced currents, or radiation before structural forces became important. There is not one magical boundary where space changes from safe to unsafe. Instead, there are layers of increasing hostility. Far away, the magnetar is a source of signals. Closer in, it becomes a hazard to instruments. Closer still, it becomes a hazard to materials. Very close, ordinary matter itself loses the conditions it needs to remain ordinary. That layered danger is actually helpful for understanding the object. It reminds us that magnetars are not just powerful in one measurement. They alter the local environment across many kinds of physics: electromagnetism, gravity, radiation, plasma behavior, quantum effects, and dense matter all overlap. A magnetar is a place where the universe refuses to separate subjects neatly. In school, we might learn gravity in one section, magnetism in another, atoms in another, light in another. Near a magnetar, all those topics sit at the same table and start speaking at once. It is noisy in the equations, even if space itself is silent from far away. However, this hostility becomes information. The same magnetic field that would destroy ordinary matter nearby also produces signals we can analyze safely. The same radiation that would be deadly up close becomes a set of X-ray photons arriving at a telescope. The same gravity that bends light near the star can shape pulses and spectra. The same flares that would overwhelm a nearby spacecraft become rare events that teach us about magnetic reconnection, starquakes, and neutron star interiors. Distance turns danger into data. That may be one of astronomy's great gifts. The universe does not become gentle, but it becomes readable. It is also worth remembering that magnetars do not roam the galaxy hunting for planets. They are objects formed from massive stellar deaths, moving through space according to gravity, often isolated, often far away. They do not choose targets. They do not threaten Earth simply by existing. The closest known magnetars are still far beyond any distance where their magnetic fields could harm us directly. Even giant flares, while astonishing, spread their energy over vast distances. The famous flare from SGR 1806 Tushtuny affected Earth's upper atmosphere after crossing the galaxy. But it was not dangerous to life here. It was a scientific event, not an apocalypse. This is an important distinction, especially before sleep. Magnetars are extreme, but they are not lurking outside the window. The window may have other issues, such as a draft, but not that. If we imagine watching from a safe observatory far away, the magnetar becomes almost beautiful. A compact star rotates. Hot regions brighten and fade as they turn into view. Magnetic field lines twist through space, invisible but powerful. Bursts flicker in X-rays. Occasionally, a larger outburst changes the rhythm. The object is dangerous only if you insist on entering its neighborhood, which is also true of many things, including active volcanoes and certain family group chats. From the proper distance, a magnetar is a source of wonder. It lets us study matter, magnetism, and gravity at extremes we could never build ourselves. The thought experiment also reveals something about scale. Human bodies are adapted to Earth. We are built for one gravity, moderate temperatures, a protective atmosphere, liquid water, and electromagnetic conditions so gentle that atoms can form stable molecules. Our sense of what is normal is based on a very narrow and fortunate range. Magnetars show us how different the same universe can become when conditions shift. Matter does not have one personality. Under low pressure, it can be gas. Under familiar pressure, it can be liquid or solid. Under stellar pressure, it becomes plasma. Under neutron star pressure, it becomes nuclear matter. Under magnetar fields, even atoms are stretched toward unfamiliar forms. The universe is not strange because it breaks rules. It is strange because the rules allow far more than everyday life prepares us for. So what would happen if you got too close to a magnetar? The gentle answer is that you would not remain you for long, and neither would your spacecraft, your instruments, or the atoms politely holding everything together. But the deeper answer is more interesting. Getting too close means entering a region where gravity, radiation, and magnetism become stronger than the structures we rely on. Electronics fail. Materials charge, heat, and break. Molecules lose stability. Atoms distort. Time and light behave under strong gravity. The magnetosphere becomes an active, dangerous landscape, and the surface below is not a surface anyone can touch. A magnetar is not hostile in intention. It simply exists at an intensity ordinary matter cannot share. And because we cannot go there, we do the human thing instead. We build telescopes. We place detectors above the atmosphere. We watch for sudden flashes. We measure pulses that arrive every few seconds. We compare X-ray spectra. We catch gamma rays and radio afterglows. We infer magnetic fields from spin down. We use timing to listen to the rotation of a dead star. We study from a distance, slowly, carefully, turning danger into understanding one photon at a time. That is how magnetars become known to us. not as visited worlds, but as signals in the dark. And those signals lead naturally to the next question. If magnetars are so small, so distant, and so hidden from ordinary sight, how do astronomers find them at all? Finding a magnetar is not like looking up and spotting a bright familiar star in a constellation. You do not point a small backyard telescope toward the sky, adjust the focus, and say, there it is, the most magnetic object for several thousand light years, sitting nicely between two ordinary-looking dots. Magnetars are usually too small, too distant, too hidden by dust, and too strange in their light to be found by casual stargazing. They are not discovered because they look impressive in visible light. They are discovered because something about them misbehaves in X-rays or gamma rays. In other words, astronomers find magnetars not because magnetars are easy to see, but because they occasionally make the universe cough loudly in high-energy radiation. This is a rather important idea. The night sky your eyes see is only a narrow slice of what the universe is doing. Human eyes are tuned to visible light, which is very sensible for walking around on Earth, reading labels, admiring sunsets, and avoiding furniture in a dim hallway. But visible light is only one small band in the electromagnetic spectrum. Beyond red light lies infrared. Beyond violet lies ultraviolet. Farther still are X-rays and gamma rays, light with much higher energy than anything our eyes can detect. Magnetars often reveal themselves in these high-energy bands. They are objects whose most important behavior happens in a kind of light we cannot see without spacecraft detectors and a fair amount of patient data analysis. So the first step in finding them is not looking harder with human eyes. It is learning to look differently. Many magnetars entered astronomy through two old names: soft gamma repeaters and anomalous X-ray pulsars. These names sound a little technical, and they are. But they also tell a story. Before scientists understood that these objects were likely part of the same family, they were noticed for different reasons. One group was found because it produced repeated bursts of relatively soft gamma rays, meaning gamma rays on the lower energy side of that high energy category. These became known as soft gamma repeaters, or SGRs. The other group was found because it pulsed in X-rays with regular periods, but its energy output did not make sense under the usual explanations. These became known as anomalous X-ray pulsars, or AXPs. The word anomalous is science's polite way of saying, this thing is doing something awkward, and we would like a meeting. Soft gamma repeaters were strange because they repeated. Many high-energy explosions in the sky happen once, or at least appear as one-time events from our point of view. A supernova brightens and fades, a gamma ray burst flashes from far away and is gone. But SGRs produced bursts again and again from the same general location. That repetition was the clue. Whatever was happening, it was not simply the total destruction of the source. The object survived its outbursts. It could flare, quiet down, and flare again. That already made it unusual. If your kettle exploded every Tuesday and then returned to working order by Wednesday, you would not call that normal kettle behavior. Astronomers felt similarly about these repeating gamma ray sources, though with more equations and fewer kitchen towels. The bursts from soft gamma repeaters are usually short, often lasting fractions of a second. During active periods, a source can produce many bursts, sometimes in storms, then become quiet again for long stretches. The bursts are high-energy flashes detected by instruments designed to watch gamma rays and X-rays from space. Because Earth's atmosphere blocks most of these high-energy photons, which is excellent for life and inconvenient for observation, astronomers rely on satellites. Detectors on spacecraft can register a sudden spike, record its time, estimate its direction, and alert astronomers that something out there has changed. A magnetar can therefore announce itself not with a calm visible glow, but with a tiny, sharp, energetic knock on a detector orbiting above the atmosphere. Anomalous X-ray pulsars were puzzling in a different way. They pulsed with periods of several seconds, which suggested rotating neutron stars. That part was familiar enough. Pulsars had already taught astronomers that neutron stars can act as cosmic lighthouses, but AXPs were too bright in X-rays to be powered simply by their loss of rotational energy. Ordinary pulsars gradually slow down, and the energy lost from rotation can power their emission. For AXPs, the numbers did not add up neatly. They were isolated, or at least not obviously feeding from a companion star in the way accreting X-ray pulsars do. They were slow compared with many radio pulsars, yet shining strongly in X-rays. Something else had to be paying the energy bill, and it was not leaving a tidy receipt. The Magnetar model helped bring these two mystery groups together. The idea was that both soft gamma repeaters and anomalous X-ray pulsars could be neutron stars with extremely strong magnetic fields. The repeated bursts of SGRs came from sudden magnetic activity, crustal stress, and magnetospheric changes. The persistent X-ray glow and unusual pulsations of AXPs came from heat and energy supplied by magnetic field decay, rather than by rotation or accretion. Two categories that had once seemed separate began to look like different moods of the same kind of object. Some magnetars behave more like classic SGRs, bursting dramatically. Others behave more like AXPs, pulsing and glowing in X-rays with fewer obvious bursts. Over time, the boundary became softer. Some AXPs were seen producing bursts. Some SGRs had persistent X-ray properties like AXPs. The family resemblance became hard to ignore. This is how astronomy often works. Objects are discovered by behavior first, and only later does a deeper physical identity emerge. A thing is named for what it does before scientists fully understand what it is. Soft gamma repeater means it repeats in soft gamma rays. Anomalous X-ray pulsar means it pulsates in X-rays in a puzzling way. Magnetar means the underlying engine is magnetic. The first names are like hearing footsteps in the hallway. The later name is opening the door and realizing who has been walking around. Of course, in this case, the visitor is a city-sized neutron star with a magnetic field strong enough to deform atoms. So perhaps opening the door should remain metaphorical. Finding magnetars therefore means watching for several clues. One clue is repeated high-energy bursts from the same sky location. Another is steady or variable X-ray emission that is too luminous to be explained by ordinary rotational spin down. Another is a slow spin period, often a few seconds, combined with a rapid slowing of that spin. That spin down gives astronomers a way to estimate the magnetic field. If a neutron star's rotation is slowing unusually quickly, a strong magnetic field may be acting like a brake. Timing becomes a diagnostic tool. A detector measures pulses. Astronomers track how the pulse period changes. From that change, they infer the strength of an invisible field. It is a little like guessing the size of a hand by watching how quickly it slows a spinning top in the dark. There are also changes after outbursts. A magnetar may suddenly brighten in X-rays, then fade over weeks, months, or years. Its pulse shape may change. Its spectrum may harden or soften. Its spin-down rate may shift. These changes suggest that the magnetosphere has been rearranged or that the crust has been heated. Astronomers monitor these after effects with X-ray telescopes such as Chandra, XMM Newton, Swift, NuSTAR, and others. Each telescope sees a different part of the story. Some have sharp imaging. Some are excellent at timing. Some cover hard X-rays. Some respond quickly to transient events. A magnetar does not usually reveal everything to one instrument in one glance. It is more like a quiet suspect in a detective story where every telescope gets one useful line of testimony. Gamma ray and X-ray monitors are especially important because magnetars can activate suddenly. Instruments such as Fermi, Swift, and Integral watch large portions of the sky for bursts. When a burst is detected, the first challenge is localization. Where did it come from? Some high-energy detectors can only estimate a rough region. Follow-up observations then refine the position. If the source is known, astronomers can connect the new burst to an existing magnetar. If it is new, they search for an X-ray counterpart, a pulsing source, or a fading afterglow. The process can involve rapid communication between observatories because magnetar outbursts change quickly. Space may be ancient, but high-energy astronomy often has a surprising amount of urgency, like someone trying to catch a train made of photons. Once astronomers identify a candidate, timing becomes essential. They look for pulsations in X-rays, or sometimes radio. A magnetar may rotate once every 2, 8, or 12 seconds depending on the source. This is slow compared with many pulsars, but still remarkable when you remember the object is a neutron star containing more mass than the Sun. A signal repeating every few seconds gives a pulse period. Repeated observations show whether that period is increasing. If the star is slowing down, the rate of slowing can be used with assumptions to estimate its dipole magnetic field. This is one of the classic signatures of magnetars: long periods, large period derivatives, and high inferred magnetic fields. The clock tells on the magnetar, but not every magnetar fits the simplest pattern perfectly. Some objects have magnetar-like bursts, but lower inferred dipole fields than expected. Some high magnetic field radio pulsars share traits with magnetars. Some magnetars emit radio pulsars after outbursts, blurring the old lines between radio pulsars and magnetars. This is not a problem in the sense of a mistake. It is a sign that neutron stars are a diverse population. The universe does not always sort objects into boxes as neatly as textbooks do. Sometimes the boxes overlap, the labels peel slightly, and a source sits there behaving as if it did not read the classification scheme. Radio observations add another layer to the search. Most magnetars were discovered or studied in X-rays and gamma rays, but a few have shown radio emission, sometimes transient and unusual compared with ordinary radio pulsars. After an outburst, a magnetar may become radio bright for a time, then fade. Radio telescopes can measure pulse arrival times very precisely, track rotation, and study the surrounding environment. In the case of magnetars near the center of the Milky Way, radio signals can also tell us about the dense magnetized plasma between us and the source. The radio voice of a magnetar is not always present, but when it speaks, it can be very informative. It is a bit like a quiet neighbor suddenly calling in with details no one else had. Infrared observations can sometimes help too, although magnetars are faint at those wavelengths. A possible infrared counterpart may reveal emission from the neutron star, its magnetosphere, or perhaps a surrounding debris disk. In rare cases, visible light is usually not the main path, but deep optical and infrared imaging can help rule out companion stars or identify counterparts in crowded regions. This is especially difficult near the plane of the Milky Way, where dust, gas, and many stars clutter the view. Finding one faint object in a crowded galactic field can be like looking for a single warm crumb in a bakery at night, except the crumb occasionally emits X-rays. Distance is another challenge. To understand how bright a magnetar truly is, astronomers need to know how far away it is. Distances can be estimated in several ways: association with a supernova remnant or star cluster, absorption by interstellar gas, radio measurements, or the behavior of surrounding material.
Is it nice there?
But these estimates can be uncertain.
It is.
A source that looks moderately
really
bright
beautiful.
nearby might actually be extremely luminous far away, or vice versa. In astronomy, distance is often the hidden ruler behind every other measurement. Without it, brightness, energy, and size become harder to pin down. Magnetars, being compact and often embedded in dusty regions, do not always make this easy. They're not only extreme, they're occasionally uncooperative. Supernova remnants can provide another clue. If a magnetar sits inside or near an expanding shell of gas from a stellar explosion, that association supports the idea that it was born from the collapse of a massive star. The remnant can also help estimate the age of the system, but the association is not always simple. Neutron stars can receive kicks at birth, so a magnetar may have moved away from the center of its remnant. The remnant may be faint, old, distorted, or hidden. Sometimes there is no obvious remnant at all. Astronomers then have to use motion, age, and surrounding structures to reconstruct the object's past. The magnetar may be a runaway ember from an explosion whose smoke has already dispersed. One of the remarkable things about magnetar discovery is that it grew from confusion. Soft gamma repeaters confused astronomers because they repeated. Anomalous X-ray pulsars confused astronomers because they were too bright for their apparent energy sources. The magnetar model did not appear because the sky was tidy. It appeared because the sky was untidy in a very specific way. The repeated bursts, the strange X-ray glow, the slow pulsations, the spin down, the lack of ordinary companions, and the occasional giant flare all pointed toward neutron stars powered by magnetic energy. The objects were telling the same story in different accents. Modern surveys continue to expand that story. All sky monitors catch new transients. X-ray telescopes follow them. Radio observatories test for pulses. Archival data searches for past activity. Sometimes an object known for years under one category reveals magnetar behavior after an outburst. Sometimes a new burst leads to a previously unknown neutron star. Sometimes a source in another galaxy may be suspected of being a magnetar giant flare rather than a distant gamma ray burst. The search is not just for dots, it is for behavior through time. A magnetar may not be obvious in a single image, but its changing light gives it away. This is why astronomers do not only map the sky, they monitor it. A static sky image tells you where things are. A time domain sky tells you what things are doing. Magnetars are creatures of the time domain universe. They burst, pulse, fade, slow, glitch, brighten, and sometimes change personality. To find them, we need instruments that notice sudden events and patience to follow slow ones. We need clocks as much as cameras. A magnetar's identity is written not just in its brightness, but in its rhythm and its surprises. There is something fitting about this. A magnetar itself is small and dark by ordinary standards, but it is surrounded by invisible structure. Its magnetic field cannot be photographed directly. Its crust cannot be seen. Its interior is hidden forever from direct touch. So we find it by consequence. We see the burst and infer the stress. We see the pulse and infer the rotation. We see the spin down and infer the field. We see the afterglow and infer the rearrangement. The magnetar is known by what it does to light, matter, and time around it. It is a cosmic fingerprint pressed into X-rays. For a listener drifting towards sleep, perhaps the gentlest image is this. Somewhere in the galaxy, a dead star turns in darkness. Most of the time, it is not visible to human eyes. Around it, magnetic field lines twist through space. Its surface may hold heat from old stresses. Its crust may be quietly adjusting. Then, without warning, a small burst of high-energy light leaves the star. Years or centuries or millennia later, depending on distance, that light reaches a spacecraft above Earth. A detector registers it. A computer marks the time. Astronomers compare positions, pulses, and energies. Slowly, the hidden object gains a name, not because we saw it in the ordinary way, but because it tapped on the high-energy window. Soft gamma repeaters and anomalous X-ray pulsars were those taps, before the full picture became clear. One said, "I burst again." The other said, "I shine too strongly in X-rays." Together, they led scientists toward magnetars, neutron stars whose magnetic fields power some of the strangest activity in the sky. And even now, with the model established, magnetars still refuse to become boring. They keep revealing exceptions, transitions, radio behavior, low-field surprises, flare candidates in other galaxies, and puzzles about how their magnetic fields evolve. Finding them is not the end of the mystery. It is the beginning of better questions. If astronomers can detect magnetars through bursts, pulses, and strange X-ray behavior, why are these objects still so difficult to fully understand? What remains unknown about their interiors, their magnetic fields, their birth, their lifetimes, and their connection to other neutron stars? By the time astronomers have found a magnetar, measured its pulses, watched its bursts, and connected it to the family of soft gamma repeaters and anomalous X-ray pulsars, it may seem as though the main mystery should be solved. The object is a neutron star. Its magnetic field is enormous. Its energy comes from magnetism rather than ordinary fusion. It spins, slows, flares, and sometimes cracks. That sounds like a respectable explanation, the kind you could fold neatly, place in a drawer, and feel reasonably pleased about. But magnetars do not stay neatly folded. Just when scientists begin to understand one behavior, another one appears. One magnetar fades for years after an outburst. Another wakes up suddenly after seeming quiet. One behaves like a radio pulsar for a while, then stops. One spins down in a surprising way. Another has a magnetic field that looks too low, at least from the outside, and yet still behaves like a magnetar. They are not impossible objects, but they are deeply untidy ones. And astronomy has learned to pay attention when the universe refuses to keep its desk organized. The mystery begins with the fact that magnetars are powered by magnetic field decay. But that simple phrase hides many moving parts. A magnetic field is not a battery with a neat little percentage indicator on the side. It does not politely say 87% remaining. Estimated flare time 6,000 years. Inside a magnetar, the field may be twisted, buried, tangled, and layered through matter at densities we cannot reproduce on Earth. Part of the field may be visible from the outside as a large dipole, like the simple north-south field we often imagine. Other parts may be hidden inside the star, stronger in local patches or wound through the crust in complicated shapes. When we measure a magnetar's spin down, we estimate one part of the magnetic field, the external dipole component, but that may not tell us everything happening below the surface. It is a little like judging an entire house by looking at one window from across the street at night. You can learn something, but you should not claim to know what is in every cupboard. This is one reason that magnetars still surprise us. Their internal magnetic fields may be stronger, more tangled, or more active than the field we infer from their rotation. A magnetar can appear modest in one measurement and still hide enormous magnetic stress in its crust or interior. That matters because outbursts may be triggered by local stresses, not just by the broad field we can estimate from timing. A small region of the crust may heat, a bundle of magnetic field lines may twist, a patch of surface may brighten. To an observer on Earth, the magnetar may look as if it suddenly woke up for no obvious reason. In reality, the cause may have been building quietly for years, centuries, or longer in a place we cannot see. When a magnetar wakes up, it often does so in X-rays. A source that was faint may suddenly become much brighter. It may release short bursts. Its pulse profile may change. Its spectrum may harden, meaning it produces relatively more high-energy X-rays. Then, after the outburst, it begins to fade. That fading is one of the most revealing parts of the story. It is not just the magnetar calming down, though that is a pleasant way to imagine it. The decline in brightness carries information about how energy was deposited in the crust, how heat moves through dense matter, and how the magnetic field above the surface relaxes. Some magnetars fade over weeks, others take months or years. Some decline smoothly, others fade in stages. Some never quite return to the same level they had before. It is as if each outburst leaves a fingerprint, and astronomers have to learn how to read the smudge. There are two major ideas often used to understand this fading. One involves crustal heating. In this picture, the outburst deposits heat in the outer layers of the neutron star. Perhaps a magnetic stress shifts the crust or drives currents that warm a small region. That hotspot then cools over time, radiating X-rays into space. As the heat leaks outward and spreads inward, the observed brightness gradually drops. The way it drops depends on how deep the heat was placed, how much energy was added, and how easily heat travels through the crust. If the heating was shallow, the source may cool relatively quickly. If it reached deeper layers, the glow may last much longer. Watching a magnetar fade is therefore a little like watching a warm stone cool after sunset, except the stone is nuclear matter. The sunset was a magnetic outburst, and the thermometer is an X-ray telescope in orbit. Another idea involves the untwisting of the magnetosphere. A magnetar's magnetic field can be twisted by movement at the surface or within the crust. When field lines are twisted, electric currents may flow along them, heating the surface where they return and scattering X-rays as they escape. Over time, the twisted bundle of field lines can relax. As it untwists, the currents weaken, the hot region shrinks or cools, and the X-ray brightness fades. This model helps explain why some outbursts show changing pulse shapes and spectra, as if the geometry of the emitting region is being rearranged. The magnetar is not merely cooling like a hot coal. Its magnetic environment is changing shape. The difficulty is that both ideas can be true at once. Heat can be placed in the crust while the magnetosphere also twists and untwists. The crust can drive the magnetosphere, and the magnetosphere can affect how radiation escapes. A flare may involve a fracture, a plastic shift, magnetic reconnection, particle acceleration, and surface heating in one connected event. Separating these ingredients from far away is hard. Astronomers receive photons, not a neatly labeled diagram. They measure light curves, pulse profiles, spectra, and timing behavior, then compare those measurements with models. The models improve, but the magnetar keeps some privacy. It is hard to blame it. If you are a city-sized remnant of a supernova with a magnetic field that could deform atoms, you might also prefer not to explain yourself fully. The waking up behavior is especially mysterious, because magnetars can be quiet for a long time. Some are discovered only when they burst. Before the outburst, the same object may have been too faint to notice, or may have sat unnoticed in archival data. Then suddenly it becomes bright enough for several telescopes to observe. This makes magnetars part of what astronomers call the transient universe, the universe of things that change. In the old picture of astronomy, stars were often treated as fixed points, and the sky was a map. In the modern picture, the sky is also a weather report. Things flare, merge, explode, pulse, disappear, and return. Magnetars belong beautifully to that restless sky. They are not always visible because they are not always active. Sometimes the only way to find one is to be watching when it wakes. One famous recent example is SGR 1935 plus 254, a magnetar in our own Milky Way. It had been known before, but in April 2020 it entered a period of intense activity. It produced many rapid X-ray bursts, and then one event arrived with both an X-ray burst and a very bright radio burst. That radio burst was important because it resembled the fast radio bursts seen from other galaxies, suggesting that magnetars can produce at least some of those mysterious radio flashes. This did not solve every fast radio burst, because the universe rarely hands over all the answers in one envelope, but it gave astronomers a nearby example of a magnetar producing a radio burst powerful enough to connect two fields of study. A magnetar woke up, and in doing so, it helped explain a mystery much larger than itself. That is another reason magnetars remain important. They do not only raise questions about neutron stars, they may also connect to other high-energy phenomena. Some fast radio bursts may come from magnetars. Some short gamma-ray bursts from nearby galaxies may be giant magnetar flares mistaken for more distant explosions. Magnetars may power some unusually bright supernovae if they are born spinning rapidly and inject energy into the expanding debris. They may also teach us about the behavior of matter at nuclear density, the strength of neutron star crusts, and the physics of extreme magnetic fields. A magnetar is not one mystery sitting alone. It is a knot where several mysteries tie together. Pull on one thread, and half the high-energy universe wiggles. Even their rotation can be strange. Ordinary pulsars sometimes experience glitches, sudden spin-ups thought to involve the interaction between the crust and the superfluid interior. Magnetars can glitch too, but they can also do surprising things around outbursts. The Magnetar 1E2259 plus 586 showed an abrupt spin-down event, often called an anti-glitch, which caught scientists' attention because neutron stars more commonly show sudden spin-ups. An anti-glitch suggests that the star's rotation and magnetic environment can interact in ways that are still not fully understood. Was it caused by changes inside the star, a sudden alteration in the external magnetosphere, some combination? The event became another reminder that magnetars are not just stronger pulsars. Their magnetic fields can complicate even the clockwork behavior of a rotating neutron star. The interior adds another layer of uncertainty. A neutron star may contain superfluid neutrons, superconducting protons, extremely dense crust, and perhaps more exotic forms deeper down. We do not know the exact equation of state, the relationship between pressure, density, and composition inside the star. That equation of state determines how large neutron stars are for a given mass, how their crusts behave, and how their interiors respond to stress. Magnetars give scientists clues, but those clues are indirect. A flare may make the star ring. Cooling may reveal the crust's thermal properties. Spin changes may reveal internal coupling, but no single observation simply opens the star and shows the answer. The interior remains hidden, and every outburst is like hearing a sound from behind a locked door. The magnetic field itself also evolves over time. Magnetars are usually thought to be most active when they are young, perhaps thousands to tens of thousands of years old, though age estimates are not always simple. As the magnetic field decays, it releases energy powering X-ray emission and bursts. Over longer periods, the field weakens, the star cools, and the object may become quieter. This raises a fascinating possibility. The galaxy may contain many old, faded magnetars that no longer announce themselves dramatically. They may be sitting quietly among the broader neutron star population, their most violent years behind them. If so, the magnetars we observe are only the visible, active tip of a much larger family. The quiet ones are like old campfires under ash, still part of the story even after the flames have gone. But even the word old becomes slippery with magnetars. Some sources behave like magnetars despite having lower inferred dipole magnetic fields than classical magnetars. SGR 0418 plus 5729, for example, has been studied as a low magnetic field magnetar, meaning its external dipole field appears much weaker than expected, yet it produced magnetar-like outbursts. This suggests that strong hidden internal fields or local magnetic structures may matter more than the broad external field alone. In other words, a magnetar can sometimes wear a quiet-looking outer coat while carrying a storm underneath. That makes classification harder, but also more interesting. The universe is reminding us not to trust only the largest, simplest measurement. Then there is the question of why some magnetars become radio emitters and others do not. A few magnetars have produced radio pulses, often after X-ray outbursts, but their radio behavior can be temporary, variable, and different from ordinary radio pulsars. The connection between X-ray activity, magnetospheric currents, particle acceleration, and radio emission is still being worked out. Radio waves are low energy compared with X-rays and gamma rays, but they can carry extremely precise timing information. When a magnetar speaks in radio, astronomers listen closely, because the pulse arrival times can reveal rotation, glitches, and changes in the magnetosphere. But the radio voice may fade, the source may become quiet again. It is less like a steady lighthouse and more like a lighthouse that occasionally decides it would prefer to be a thundercloud. Magnetars also challenge our understanding because they are rare in the observed sky. There are only a few dozen confirmed or strong candidate magnetars known in the Milky Way and nearby galaxies. That is enough to study patterns, but not enough to make every question easy. Each source can have its own personality. Some are very active, some are quiet, some burst often, some produce giant flares, some show radio emission, some live inside supernova remnants, some appear isolated, some may be older than expected. With small samples, every new object can change the picture. Astronomers have to be careful not to mistake one magnetar's habits for the whole family's rules. A small group of extreme dead stars can be very bad at representing itself politely. Observation is also limited by the instruments available at the moment an event occurs. Magnetar outbursts can happen suddenly. A satellite may be looking elsewhere. A detector may saturate during the brightest part. The source may be near the sun in the sky from Earth's point of view and hard to observe. Follow-up may begin hours or days later. The first moments, which might contain crucial clues, can be partly missed. Astronomers work around this with all-sky monitors, rapid alerts, and coordinated observations. But nature does not always wait for the observing proposal to be approved. A magnetar can wake up at inconvenient times, which is perhaps the most human thing about it. Even when observations are excellent, interpreting them takes care. A fading X-ray light curve could be explained by crustal cooling, magnetospheric untwisting, or a combination. A change in pulse shape could mean a hot spot moved, a new spot appeared, or scattering in the magnetosphere changed. A burst storm could come from many small crustal failures or magnetospheric reconnection events. A spin change could involve internal superfluid motion or external torque changes. Each explanation must be tested against the data, and often several remain possible. This does not mean scientists know nothing. It means they know enough to ask precise questions, but the object is complex enough that one clean answer may be too simple. There is also the matter of scale. Magnetars force us to connect tiny nuclear physics with enormous astronomical events. The behavior of nuclei in the crust may affect a flare seen across the galaxy. The motion of charged particles a few kilometers above the surface may shape a radio burst detected thousands of light years away. The decay of magnetic fields inside a city-sized remnant may influence high-energy transients in other galaxies. It is all connected across scales that do not fit comfortably in the mind. A magnetar is small in size, massive in content, extreme in field strength, brief in bursts, long in influence, and stubborn in mystery. It refuses to be understood at only one level. Why do magnetars fade? Because the energy from an outburst is gradually radiated away. Because heated regions cool, because magnetic twists relax, because currents weaken, and because the star returns toward a quieter state. Why do they change? Because their magnetic fields evolve, their crusts respond, their magnetospheres rearrange, and their rotation couples to hidden internal motion. Why do they wake up again? Because the magnetic field is still not fully settled, stress can build again. A quiet surface can hide deep tension. A star that appears dormant may still carry stored magnetic energy, waiting for the right shift. The magnetar is not alive, but it has cycles of activity and rest, and from far away those cycles can feel almost like sleep and waking. That comparison is only a metaphor, of course. A magnetar does not dream. It does not choose to rest or stir. Its quiet phases are physical states, not moods. But for us watching from a small planet, the rhythm is hard not to notice. A source fades into near silence. Years pass. Instruments keep watch. Then a burst appears. The hidden star announces that something changed. The old magnetic heart is still active. And once again, astronomers turn their telescopes toward it, gathering X-rays, timing pulses, measuring spectra, and trying to learn what moved in a place no spacecraft could survive. This is why magnetars remain one of astronomy's deepest mysteries. We have a broad explanation, but the details are rich and unsettled. We know they are neutron stars with extreme magnetic fields, but not exactly why some neutron stars become magnetars and others do not. We know magnetic energy powers their activity, but not every detail of how that energy moves from interior field to crust to magnetosphere to radiation. We know they fade after outbursts, but the cooling and untwisting can differ from source to source. We know some wake up after years of quiet, but predicting when remains beyond us. We know they may connect to fast radio bursts and powerful transients, but the full relationship is still being mapped. And that is not a weakness in the story. It is the reason the story is still alive. A completely solved magnetar would be impressive, but a partially understood magnetar keeps calling us back. It asks about matter, magnetism, gravity, time, radiation, and stellar death all at once. It reminds us that the universe is not divided into easy subjects. A dead star can become a laboratory, a burst can become a message, a fading glow can become a measurement of hidden heat. A sudden wake-up can change what we think radio bursts are. Somewhere inside the darkness, a magnetar turns every few seconds. Quieter now, perhaps, or building toward its next surprise. And the more we learn from its changes, the closer we come to the final question of this journey. What do these strange magnetic remnants reveal about the larger life and death of stars, and about the hidden power still waiting inside the universe after the bright flames have gone out? After spending time with magnetars, it becomes clear that they are not just unusual objects tucked away in the stranger corners of astronomy. They are reminders, very dense reminders, admittedly, and not the kind you would stick to the refrigerator unless the refrigerator had already become a thin cloud of charged particles. But reminders all the same. They remind us that a star's death is not always a quiet fading. They remind us that gravity can crush matter into forms almost beyond recognition. They remind us that magnetism, a force we usually meet in small and useful ways, can become one of the dominant powers in the life of a dead star. And perhaps most importantly, they remind us that the universe often hides its greatest intensity in places too small to notice with ordinary eyes. A magnetar begins as part of a much larger story. It is not born separately from the rest of cosmic history. It comes from a massive star, a star that once shone with fusion in its core, made heavier elements in its layers, and lived under the old balance between pressure and gravity. For a while, that balance holds. The star shines, it sends light into space, it may warm nearby gas, it may help sculpt a star-forming region, it may be one of many bright stars in a cluster, all young, hot, and rather dramatic in the way massive stars tend to be. Then the core changes. Fuel runs out, iron builds up, pressure fails, gravity takes over, the outer star explodes, and the inner core collapses. Out of that violent ending, under the right conditions, a magnetar can remain. This tells us something important about death in the universe. Death is not always disappearance. In astronomy, death often means transformation. A neutron star can cool, spin, pulse, flare, or, in the case of a magnetar, carry a magnetic field so powerful that it keeps shaping the object long after fusion has stopped. The original star is gone, but its consequences continue. In that sense, a magnetar is not a simple ending. It is a compact afterlife of stellar physics, a place where the last moments of a star remain stored in gravity, density, rotation, and magnetic energy. That idea is useful because it changes how we think about the night sky. The stars we see are not permanent decorations. They are temporary arrangements of matter and energy. Some are young, some are old. Some will fade gently, some will explode, some will leave white dwarfs, some will leave neutron stars, some will make black holes. And among the neutron stars, a few become magnetars, the rare remnants whose magnetic fields dominate their future. So when we study a magnetar, we are not only studying a strange object, we're studying what massive stars can become when their lives are pushed all the way to the edge of collapse. Gravity is one of the first lessons magnetars teach clearly. A magnetar is only about the size of a city, yet it can contain more mass than the sun. That single fact is enough to make everyday intuition step aside. On Earth, large things are usually heavy, and small things are usually manageable. A suitcase can be heavy, yes, especially if someone packed for a weekend as though they were relocating permanently. But size and weight still have a familiar relationship. Neutron stars break that habit of thought. They tell us that mass can be compressed into a region so small that the object becomes compact in a way no ordinary matter can imitate. Gravity does not need size to be powerful. It needs mass packed tightly enough. Around a magnetar, gravity curves space-time strongly. Light leaving the surface loses energy as it climbs away. The path of light bends. Time itself ticks differently near the star compared with far away. These effects are not optional decorations on the story. They are part of what the object is. Einstein's general relativity, which can seem distant from daily life, becomes practical near neutron stars. A magnetar is a place where gravity is not merely a downward pull, but a shaping of space and time around an extremely compact body. We cannot stand there and watch a clock run slow, and for several reasons we should be thankful for that. But the physics is still real. Every photon escaping from the surface carries the mark of strong gravity. The matter inside a magnetar is another lesson. We know matter as solids, liquids, gases, and plasmas. We know rocks, water, air, metal, wood, ice, skin, glass, and all the ordinary textures of life. A neutron star asks what matter becomes when gravity crushes atoms until their normal structure is no longer the main story. Electrons and protons combine, neutrons dominate. The crust may contain neutron-rich nuclei arranged in a dense lattice. Deeper inside, neutron superfluids, superconducting components, and possibly more exotic forms of matter may appear. Scientists do not yet know the full answer. The interior of a neutron star is one of the hardest places in the universe to understand, not because it is vague, but because it is too extreme for direct experiment. This is why magnetars are valuable as laboratories. Not laboratories with clean benches, safety goggles, and someone labeling every drawer, but natural laboratories. They let physicists test ideas about dense matter, nuclear forces, heat flow, crust strength, and the behavior of particles under immense pressure. When a magnetar cools after an outburst, the fading X-ray light can reveal how heat moves through its crust. When a flare shows oscillations, those patterns may tell us about vibrations in the star. When timing measurements show sudden spin changes, they may reveal interactions between the crust and the hidden interior. A magnetar is too far away to touch, but it still gives information. It turns extreme conditions into signals. Then there is magnetism. Magnetars teach us that magnetic fields are not always gentle guides for compass needles. In daily life, magnetism is mostly helpful, or at least harmless. It lets motors work. It helps generators produce electricity. It points compasses north. It lets a magnet hold a node on the fridge, assuming the node is not too ambitious. Earth's magnetic field helps protect the planet from charged particles from the sun. The sun's magnetic field shapes sunspots and solar flares. Magnetic fields are everywhere in astronomy, threading planets, stars, disks, jets, galaxies, and interstellar gas. But in magnetars, magnetism reaches a level that changes the identity of the star itself. The magnetic field of a magnetar is not only strong, it is active. It stores energy. It stresses the crust. It heats the surface. It twists the magnetosphere. It powers persistent X-ray emission and sudden bursts. It slows the star's rotation. It may deform atoms nearby and influence the way light travels through the region close to the surface. In most stars, fusion is the main power source. In magnetars, fusion is gone. The magnetic field takes over as the driver of visible activity. This is a very strange kind of stellar afterlife. A star that no longer shines by burning fuel, but by slowly rearranging the magnetic energy left in its collapsed core. This also helps scientists understand other neutron stars. Magnetars are not completely separate from pulsars, rotating radio transients, central compact objects, or other neutron star types. They may be part of a broader neutron star family with different magnetic fields, ages, rotation rates, and evolutionary paths. Some high magnetic field pulsars show magnetar-like behavior. Some magnetars emit radio pulses. Some objects blur the boundaries. This matters because nature rarely creates categories for our convenience. The more astronomers study magnetars, the more they learn that neutron stars may move through different phases or reveal different behavior depending on their magnetic field, internal structure, age, and surroundings. A magnetar may be an extreme member of the family, but studying the extreme helps us understand the ordinary. Magnetars may also connect to some of the brightest and fastest events in the universe. Their giant flares can resemble short gamma-ray bursts if seen from far away. A newborn, rapidly spinning magnetar may help power some superluminous supernovae, making a stellar explosion far brighter than usual by injecting energy into the expanding debris. Magnetars may produce at least some fast radio bursts, as shown by the connection between a galactic magnetar and a bright radio burst in 2020. None of this means magnetars explain every mysterious flash in the sky. The universe has more than one way to be dramatic. But magnetars have become serious candidates in several major astrophysical puzzles, which is impressive for objects only about the size of a city. They also reveal something about hidden power. A magnetar can look small, dim, or quiet for long periods. Then it can suddenly release a burst that changes how telescopes see the high-energy sky. That is because its power is not obvious in visible light. It is stored in the magnetic field, in the dense crust, in the twisted magnetosphere, in structures that cannot be seen directly. The object's visible appearance does not advertise its full capacity. This is common in astrophysics. A black hole is known by its effects. Dark matter is inferred by gravity. Exoplanets are often found by tiny dips in starlight or slight stellar wobbles. Magnetars join this tradition. They are known by consequences: a pulse, a flare, a fading X-ray glow, a sudden radio burst. The hidden thing becomes visible by what it does. There is comfort in this, strangely enough. Not comfort because magnetars are gentle, but because the universe is understandable even when it is extreme. We do not need to travel to a magnetar to learn from it. We do not need to survive its gravity or its radiation. Magnetars also put our own world into perspective. Here, the magnetic field is mild. Gravity is comfortable enough for walking, sitting, sleeping, and occasionally dropping things in a way that is annoying but survivable. Atoms behave consistently. Water can be liquid. That may be one of the deepest things magnetars reveal. The universe has range. It can make soft clouds and nuclear density crusts. It can make compass needles and quadrillion Gauss fields. It can make a star shine for millions of years, then crush its core in seconds. It can make life possible in one place and impossible in another, not by changing the rules, but by changing the conditions. Physics is the same, but the outcomes differ wildly. A magnetar is not supernatural. It is not magic. It is ordinary physics under extraordinary pressure, ordinary magnetism pushed to an extraordinary scale, ordinary stellar death followed into an extraordinary remnant. They also remind us that many endings are not simple. When a massive star dies, its story does not end at the explosion. The supernova remnant expands. Heavy elements mix into space. A neutron star may race away from the center. A magnetar may flare thousands of years later. For the people studying them, magnetars are both solved and unsolved. We know enough to say what they are in broad terms. Highly magnetized neutron stars whose activity is powered by magnetic energy, but the details remain rich. How exactly are their magnetic fields created? Why do some neutron stars become magnetars while others become ordinary pulsars? What is the exact structure of their interiors? How does the crust fail? How does the magnetosphere store and release energy? Which fast radio bursts come from magnetars and which do not? How many old, quiet magnetars are hidden in the galaxy? These questions keep the field alive. They make magnetars not only objects of awe, but active tools for discovery, and perhaps that is the best place to leave them. Not as monsters, not as cosmic threats, not as science fiction decorations, but as teachers. They teach us about the death of massive stars. They teach us about gravity near the edge of collapse. They teach us about matter squeezed to densities far beyond Earth. They teach us about magnetic fields that can power radiation long after fusion has ended. They teach us about patience because many reveal themselves only when they wake. They teach us about humility because even after decades of study, they still surprise us. So as we come back from the far side of this magnetic story, imagine the sky again. Not as empty and not as still, but as full of quiet remnants. Somewhere out there, a magnetar rotates slowly, perhaps once every few seconds. Its surface is small, its gravity immense, its magnetic field twisted through darkness. It may be quiet tonight. It may have been quiet for years, or it may be building stress in a crust harder than steel, waiting for some hidden threshold to be crossed. If it flares, the light will leave at once, racing outward through the galaxy. If it is far enough away, it will become no danger, only information. One day that signal may reach a telescope above Earth, and someone will see the data and know that the dead star has stirred again. And here, far from that extreme place, you're safe in a much gentler field. Earth turns beneath you. Its magnetic shield surrounds you quietly. Gravity holds you softly enough to rest. The atoms in your body remain atoms. The room around you stays ordinary, which, after learning about magnetars, feels like a small miracle of its own. If this journey through dead stars and magnetic hearts has brought you a little calm or a little wonder, then perhaps that is enough for tonight. The universe can be fierce beyond imagining, but from here we can meet that fierceness slowly, through science, through curiosity, and through the simple comfort of understanding one strange thing a little better than before. Sleep well, fellow traveler, wherever you are beneath the turning sky. Somewhere in the dark, magnetars keep their hidden power. Stars remember their violent endings, and the quiet light of distant physics continues crossing space on its way to anyone patient enough to listen.